Not every mystery is hidden beneath the ground. Some have towered above us for thousands of years, daring every generation to explain them. Across the ancient world, remarkable monuments still stand with a precision, scale, and durability that often seem impossible for their time. Their stones can be measured, their age estimated, and their ruins carefully mapped. But the knowledge that transformed raw landscapes into these extraordinary places remains frustratingly incomplete. Each new discovery uncovers another fragment of the story, yet the full picture never seems to emerge. Perhaps these monuments were never meant to leave us with answers. Perhaps they were always destined to leave us with questions that time itself could not erase. Located about 100 kilometers northeast of Palmyra in the Syrian desert, Qasr al-Hayr al-Sharqi is an immense Umayyad complex whose walls have quietly resisted one of the harshest environments on Earth for nearly 13 centuries. What continues to puzzle researchers is not simply why it survived, but whether the builders possessed knowledge of construction materials whose full composition can no longer be reconstructed. The ruins first attracted serious archaeological attention during the early 20th century, with systematic excavations led by Syrian and international teams beginning in the 1960s. What emerged beneath drifting desert sand was far more than an isolated palace. Covering nearly 7 square kilometers, the site included fortified walls, residential quarters, workshops, baths, mosques, irrigation canals, reservoirs, and agricultural installations, revealing a carefully planned desert settlement established around AD 728 to 729 under the Umayyad Caliph Hisham ibn Abd al-Malik. Yet despite centuries of exposure to intense solar radiation, violent sandstorms, seasonal flash floods, and annual temperature fluctuations ranging from below freezing winter nights to summer highs exceeding 45 degrees Celsius, substantial sections of masonry remain remarkably stable, directing attention toward the materials themselves rather than simply the architecture. At first glance, the construction appears conventional. Limestone forms the majority of the walls, while basalt, gypsum, reused marble, and fired bricks appear throughout different parts of the complex. However, detailed examination quickly reveals that these materials were never used randomly. Individual stone types seem deliberately selected for specific structural roles, suggesting that the builders understood their mechanical behavior in ways that written records never describe. Some limestone blocks display extensive surface weathering, while the mortar joints between them remain unexpectedly intact, implying that the binding material may have been engineered to compensate for the stone's weaknesses. Modern laboratory analyses have identified lime-based mortar mixed with gypsum and locally available mineral aggregates, yet the exact proportions remain uncertain because centuries of chemical alteration have modified the original composition. Unlike modern cement, whose ingredients can usually be reconstructed with precision, these ancient mixtures have undergone continuous reactions with groundwater, airborne salts, and desert humidity, obscuring the original formula. The greatest mystery, however, lies not inside the mortar but across the surfaces that once covered almost every interior wall. Archaeologists have discovered surviving layers of desert plaster that continue adhering tightly after nearly 1,300 years, even where surrounding masonry has partially collapsed. Under microscopic examination, these coatings appear far more sophisticated than ordinary gypsum plaster. Chemical studies have identified gypsum crystals, lime particles, clay minerals, and traces of silicate compounds, yet several samples also contain microscopic organic residues that remain difficult to identify. Because the surviving concentrations are extremely small and heavily degraded, researchers cannot determine with certainty whether the builders intentionally added plant resins, animal proteins, natural oils, tree gums, or other organic binders to strengthen the mixture. Every proposed ingredient has experimental support, but none explains all of the chemical signatures preserved inside the plaster. As analytical techniques become more sensitive, the mystery has only deepened, because each newly detected compound introduces another possible recipe rather than confirming a single one. That uncertainty becomes even more significant when the plaster's physical performance is considered. Ordinary gypsum coatings exposed to repeated thermal expansion, salt crystallization, and abrasive sand typically fracture, powder, or detach within decades if left unmaintained. At Qasr el-Hayr el-Sharqi, however, portions of the original coating remain firmly bonded to masonry, despite nearly 13 centuries of uninterrupted environmental stress. Laboratory measurements indicate that some surviving layers possess unusually low permeability, allowing limited moisture penetration while still remaining sufficiently porous to release trapped water before internal pressure builds. Such behavior is extremely difficult to reproduce without carefully balancing the proportions of mineral and organic additives. Modern conservation specialists attempting to recreate comparable mixtures have produced visually similar plasters, yet none has consistently matched both the adhesion and long-term durability observed in the original material. As researchers continued sampling different buildings across the settlement, another unexpected pattern emerged. The plaster composition varies slightly from structure to structure, yet the overall performance remains remarkably consistent. This suggests that the builders may not have followed a rigid written formula, but instead relied on a sophisticated tradition of material preparation passed directly between craftsmen. Such practical knowledge often disappears within only a few generations once construction ceases, leaving behind finished monuments, but not the techniques that created them. No surviving Umayyad manuscript describes how these plaster mixtures were prepared, how long they were cured, how finely minerals were ground, or in what sequence ingredients were combined. Without those details, even advanced chemical analysis cannot fully reconstruct the manufacturing process. The mortar presents a similar challenge. Samples collected from foundations, defensive walls, bathhouses, and residential buildings reveal subtle differences in mineral composition that appear intentional rather than accidental. Some mixtures contain higher concentrations of gypsum, while others are richer in lime or volcanic particles transported from distant regions. These variations imply that the builders adjusted their recipes according to structural requirements, instead of applying one universal mixture throughout the complex. Such adaptive material engineering resembles modern construction practices far more closely than previously assumed. Yet the reasoning behind each variation remains largely speculative, because no contemporary documentation survives. Environmental chemistry adds another layer to the puzzle. Desert soils surrounding the site contain soluble salts capable of migrating into masonry through moisture. As these salts crystallize, they normally generate enough pressure to crack stone, separate mortar joints, and detach plaster from walls. This process has destroyed countless archaeological sites across the Middle East. Yet certain sections of Qasr el-Hayr el-Sharqi display surprisingly limited salt damage despite centuries of exposure. Some researchers suspect that the mortar's internal pore structure allowed salts to crystallize harmlessly within microscopic voids rather than against vulnerable surfaces. Others argue that unidentified additives altered moisture movement through the walls, reducing destructive crystallization altogether. Neither hypothesis has been conclusively demonstrated because the original material continues changing chemically after every seasonal cycle. Equally intriguing is the complex relationship between the construction materials and the desert climate. Thick masonry certainly helps stabilize indoor temperatures, but thermal imaging suggests that the wall coatings themselves also contributed significantly to passive cooling. Mineral composition influences how much solar radiation is absorbed, reflected, or slowly released after sunset. The surviving plaster appears to moderate heat transfer more effectively than simple gypsum coatings reproduced in modern experiments, raising the possibility that its unusual composition improved both structural durability and thermal performance simultaneously. If so, the lost recipe represented not merely decoration, but an integrated environmental technology designed specifically for one of the most demanding climates in the ancient world. Even the reused building materials introduce unanswered questions. Decorative marble columns and carved architectural blocks incorporated into the complex originated from earlier Roman and Byzantine structures scattered across Syria. While isotopic analysis has identified several possible quarry regions, archaeologists still cannot determine exactly which abandoned monuments supplied many of these stones, or why particular materials were selected for specific locations within the palace. The builders may have chosen them simply for availability, yet the repeated association between certain recycled stones and structurally demanding areas suggests that durability may have influenced those decisions as well. In the heart of modern Rome, Italy, the markets of Trajan still preserve a construction secret that has survived nearly 2,000 years. At first glance, the site appears to be an ordinary complex of red brick walls, yet it may actually contain one of the ancient world's least understood building materials. The structure was built between approximately 100 and 110 AD, during the reign of Emperor Trajan, with the overall project traditionally attributed to the architect Apollodorus of Damascus. Although portions of the complex remained visible throughout the Middle Ages, systematic archaeological investigation only began during the 19th century and expanded dramatically during the large-scale excavations of the 1920s and 1930s, when layers of later construction were removed to expose an extraordinary multi-level complex stretching across the slope of the Quirinal Hill. Archaeologists expected to find another impressive Roman monument, yet what emerged was something far more remarkable. Over 150 interconnected rooms, corridors, vaulted halls and terraces, all supported by construction materials whose long-term performance continues to surprise modern engineers. Every new laboratory analysis has revealed more about the ingredients used by Roman builders, but the closer scientists examine the materials, the more difficult it becomes to explain why they have remained so durable after nearly 20 centuries. Attention usually focuses on Roman concrete, yet one of the greatest mysteries of the markets of Trajan is not hidden inside the concrete itself, but in the countless deep red bricks that cover almost every wall. More than decorative facing, these bricks function as an integral structural system, locking into the concrete core and distributing enormous loads throughout the building. Their remarkable preservation has puzzled researchers because they have experienced nearly 2,000 years of earthquakes, seasonal temperature changes, rainfall, pollution, and repeated human occupation, yet many remain astonishingly intact. Modern laboratory studies show that their mineral composition varies more than expected, suggesting they were not all manufactured from identical clay sources. Some contain unusually high concentrations of iron-rich minerals that produce their characteristic dark red color, while others contain volcanic inclusions, microscopic feldspar crystals, or different proportions of quartz that should have caused inconsistent firing behavior. Instead, the finished products display an extraordinary uniformity in strength and appearance. Even more intriguing, many bricks exhibit vitrified surfaces formed during firing, indicating temperatures that may have exceeded. 850 to 950 degrees Celsius. But no written Roman source explains how such temperatures were consistently maintained across thousands of individual bricks without modern kilns or temperature monitoring. Archaeologists have reconstructed ancient furnaces, yet none can fully explain how production remained so standardized over projects requiring hundreds of thousands of bricks. The precision suggests a manufacturing system governed by technical knowledge that disappeared long before detailed records could preserve it. As researchers continued investigating the brickwork, another mystery emerged beneath the surface, where the bricks meet the mortar and concrete. Rather than acting as separate materials, microscopic examination shows that the interfaces between them have gradually evolved over centuries through slow chemical reactions. Minerals rich in calcium, aluminum, and silica formed new crystalline structures that strengthened the connections instead of weakening them. Unlike modern Portland cement, which generally deteriorates once cracking begins, the Roman matrix appears capable of continuing its chemical development long after construction ended. Recent studies have identified complex calcium-aluminum silicate hydrates, together with rare mineral phases such as stratlingite and hydrotalcite, that improve durability and reduce internal stresses. Exactly how Roman builders encouraged these reactions remains uncertain, because surviving ancient texts describe construction methods only in general terms and never provide precise recipes or proportions. Scientists know the principal ingredients included lime, volcanic pozzolana, crushed brick, and stone aggregates. But knowing the ingredients has proven very different from understanding the manufacturing process itself. Small differences in mixing temperature, moisture content, curing conditions, or the sequence in which materials were combined may have fundamentally altered the resulting chemistry. Yet those practical details have largely vanished from history. This uncertainty becomes even more striking when examining the concrete hidden behind the brick facades. Modern analysis has revealed that Roman builders intentionally altered the density of their concrete depending on where it would be used. Lower sections supporting the greatest weight incorporated heavier volcanic stones and dense aggregates, while upper levels increasingly relied on lighter volcanic tuff and porous materials that significantly reduced structural loads. Such careful variation demonstrates an advanced understanding of material performance centuries before structural engineering became a formal science. The markets of Trajan rise through multiple terraces connected by barrel vaults, groin vaults, and massive retaining walls embedded directly into the hillside, creating enormous internal stresses that should have produced widespread structural failure. Instead, much of the original framework remains standing. Researchers still debate whether Roman builders developed empirical formulas governing aggregate selection or relied entirely on generations of accumulated craftsmanship. No surviving manuscript explains how these material transitions were calculated, leaving engineers to reconstruct ancient decisions only through physical evidence preserved within the walls themselves. The more scientists investigate the concrete, the more another unexpected phenomenon attracts attention. Numerous samples contain irregular white fragments known as lime clasts that were once dismissed as evidence of poor mixing. Modern research suggests the opposite may be true. These fragments appear capable of dissolving when water penetrates microscopic cracks, releasing calcium that reacts with dissolved carbonates and gradually seals portions of the damaged material. Laboratory experiments have demonstrated measurable self-healing behavior under controlled conditions, yet researchers still disagree about whether Roman builders intentionally created this mechanism through hot mixing techniques or whether it emerged accidentally from ancient production methods. Even if the process was deliberate, no surviving description explains how workers consistently generated these reactive inclusions across large construction projects like the markets of Trajan, the ancient recipe remains incomplete despite decades of mineralogical analysis using scanning electron microscopy, X-ray diffraction, and isotopic chemistry. These unanswered questions become even more significant when considering the building's remarkable resistance to time itself. Rome has experienced repeated seismic events throughout its history, including earthquakes that damaged countless other monuments. The markets of Trajan certainly suffered partial collapses and later modifications, yet substantial portions of the original structural core remain remarkably stable. Engineers believe the explanation lies not in any single material, but in the interaction between brick, mortar, concrete, and volcanic aggregate, each possessing different mechanical properties that allowed stresses to disperse rather than concentrate. However, reproducing this balance has proven exceptionally difficult. Modern concrete can often achieve greater compressive strength immediately after curing, but matching the long-term durability and chemical resilience demonstrated by Roman construction has remained a persistent challenge. Researchers can identify most of the raw materials with considerable confidence, yet they still cannot recreate the exact sequence of choices that transformed ordinary volcanic ash, lime, clay, and stone into a building system capable of surviving almost 20 centuries. In the ancient city of Butrint in southern Albania, only a few kilometers from the Ionian Sea, stands a circular Roman baptistery, whose floor appears to ignore everything modern engineers expect from stone, mortar, and time. Built in an environment where groundwater constantly rises beneath the foundations, surrounded by wetlands saturated with moisture and salt, the structure should have suffered extensive cracking and the complete loss of its decorative pavement centuries ago. Instead, one of the largest surviving early Christian mosaics in the Balkans remains remarkably intact, raising a question that archaeology still cannot fully answer. What exactly did its builders mix into the materials beneath the floor to make them survive for more than 15 centuries? The baptistery came to modern attention after systematic excavations began at Butrint in 1928, under the Italian archaeologist Luigi Maria Ugolini. Beneath centuries of collapse and sediment, archaeologists uncovered the remains of a monumental circular baptismal building, dating primarily to the 6th century AD, constructed during the reign of the Eastern Roman, or Byzantine, Empire. Measuring approximately 13.5 meters in diameter, the building contained an elaborate mosaic floor composed of hundreds of thousands of carefully cut tesserae, arranged into intricate geometric patterns surrounding symbolic animals and Christian imagery. Yet the greatest surprise was not the artwork itself, but the extraordinary condition of the floor, despite centuries of flooding, earthquakes, abandonment, and continuous exposure to one of the most challenging environments imaginable for ancient masonry. That environment is the beginning of the mystery. Butrint sits on low coastal ground beside Lake Butrint, connected to the Ionian Sea through a narrow channel. The local water table remains unusually high throughout much of the year, allowing moisture to migrate upward through the soil by capillary action. Modern conservation studies repeatedly identify groundwater and soluble salts as the greatest threats to the monument, because dissolved chlorides and sulfates normally crystallize inside porous stone and mortar, gradually forcing the material apart from within. Across the Mediterranean, countless Roman mosaics have disappeared through precisely this process. The Butrint baptistery should have followed the same fate, yet large sections of its original pavement remain firmly attached to the foundation beneath it, suggesting that the ancient builders possessed an exceptionally durable construction system whose complete composition has never been reconstructed. The greatest puzzle lies beneath the colorful surface rather than within it. A Roman mosaic appears deceptively simple, but it depends entirely on the stability of the invisible layers underneath. The decorative tesserae themselves measure only a few centimeters across and are incapable of supporting structural loads. Their survival depends on multiple carefully prepared bedding layers consisting of coarse stone, crushed aggregate, lime mortar, and progressively finer mixtures that distribute weight while absorbing movement in the soil below. At Butrint, this entire system has remained bonded despite repeated cycles of seasonal flooding, drying, thermal expansion, and seismic activity over nearly 1,500 years. Modern engineers understand the general principles behind Roman flooring, yet the precise formulation used here continues to resist complete explanation, because laboratory analysis identifies the ingredients only in broad categories, rather than revealing the exact recipe that produced such exceptional durability. Microscopic examination of surviving mortar has confirmed the presence of lime combined with silicate-rich mineral particles capable of hydraulic reactions, meaning the material could continue hardening even in damp conditions. This characteristic immediately invites comparison with Roman hydraulic concrete, one of antiquity's greatest engineering achievements. Throughout the Roman world, volcanic ash known as pozzolana reacted chemically with lime to form calcium-aluminum silicate hydrates, producing exceptionally strong and water-resistant mortar. However, Butrint introduces a complication that researchers have yet to resolve. Albania possesses no volcanic deposits comparable to those surrounding the Bay of Naples, where the finest pozzolanic material originated. If the builders relied on imported Italian ash, transporting enormous quantities across the Adriatic would have required substantial logistical effort and expense. If they instead used local minerals capable of producing similar reactions, the precise geological source remains unidentified. Either possibility leaves an important gap in our understanding of how construction materials circulated across the late Roman Mediterranean. As researchers continued examining the floor, another inconsistency emerged. The mosaic has endured repeated environmental stresses that should have gradually separated the decorative surface from the supporting mortar. Every rise in groundwater introduces dissolved minerals into microscopic pores. Every period of drying allows those minerals to crystallize and expand. Each cycle exerts tiny pressures that accumulate over centuries until stone layers detach. Modern concrete often suffers visible delamination under far less severe conditions after only several decades. Yet the Butrint mosaic still behaves as though the bedding layers function almost as a single continuous material. Some scientists suggest that the ancient mortar developed an unusually dense internal microstructure with exceptionally low permeability, slowing the penetration of water and salts. Others propose that ongoing chemical reactions inside the mortar may have continued filling microscopic cracks with newly formed minerals, creating a limited self-healing effect, similar to processes recently documented in certain Roman marine concretes. Neither explanation has yet been demonstrated conclusively for Butrint, leaving the remarkable adhesion between mosaic and foundation one of the site's most intriguing unsolved questions. The geometry of the structure makes the mystery even more remarkable. A circular building distributes loads differently from rectangular architecture, concentrating stresses around curved walls and radial floor segments. Any uneven settlement beneath the foundation should gradually distort the geometry, producing fractures that spread outward through the mosaic. Instead, despite centuries of occupation, abandonment, earthquakes affecting the Balkans, and constant changes in groundwater levels, the baptistry's circular plan remains surprisingly stable. Archaeological investigations reveal that the floor rests upon several carefully organized construction layers rather than a single slab, indicating sophisticated knowledge of load distribution and ground preparation. Exactly how the builders determined the thickness, density, and composition of each layer without modern engineering calculations remains uncertain, particularly because the surrounding terrain consists largely of soft alluvial deposits that normally present serious foundation challenges. Conservation work has also revealed evidence that portions of the structure were repaired during later Byzantine occupation. Normally, repairs carried out decades or centuries after the original construction introduce new mortar with different mechanical properties. Differences in thermal expansion, elasticity, or moisture absorption usually create weak boundaries where cracks eventually develop. Surprisingly, many repaired areas at Butrint remain well integrated with the older construction, suggesting either that later craftsmen preserved knowledge of the original material or that they independently reproduced a remarkably compatible mixture. Archaeological science cannot yet distinguish between these possibilities because the surviving samples remain too limited to reconstruct the complete manufacturing process with certainty. Jerash, located among the rolling hills of northern Jordan, is one of the best preserved Roman cities ever discovered, yet its greatest mystery may not be its temples or colonnades, but the materials that allowed an entire city of limestone to survive nearly 2,000 years. When systematic excavations began in the early 20th century, after centuries of being buried beneath earthquake debris and accumulated soil, archaeologists expected to uncover familiar Roman engineering. Instead, they found evidence suggesting that many of the city's construction techniques relied on material formulas that are still only partially understood. As excavation expanded across more than 800,000 square meters, researchers uncovered over 600 columns, monumental gates, theaters, baths, churches, underground sewers, and one of the longest surviving colonnaded streets in the Roman world. Built primarily between the 1st and 3rd centuries AD, Jerash flourished under Roman rule, despite lying far from Italy's volcanic regions where the empire usually obtained the pozzolanic ash that produced its most durable concrete. That geographical reality immediately raised an important question. If the builders lacked easy access to the ingredients used in many famous Roman structures, what allowed Jerash to withstand almost 20 centuries of earthquakes, seasonal flooding, intense summer heat, and constant erosion? One of the most overlooked mysteries appears before visitors even notice the architecture itself. Today, the city seems almost monochrome, covered by pale golden limestone, creating the impression that ancient Jerash was designed with natural stone exposed to the sun. Archaeology tells a very different story. Microscopic pigment analysis has revealed traces of vivid red, Egyptian blue, yellow ochre, black carbon pigments, and brilliant white lime coatings on temples, gateways, and monumental columns. The famous Temple of Artemis, sections of the South Theatre, and numerous decorative capitals all preserve microscopic fragments of color invisible to casual visitors. These discoveries indicate that Jerash was once an intensely colorful city rather than the pale archaeological landscape seen today. Yet the greatest puzzle is not the pigments themselves but the substance that bonded them permanently to limestone surfaces. After nearly 2,000 years of exposure, earthquakes, moisture, ultraviolet radiation, and wind erosion, measurable traces still remain inside microscopic pores of the stone. Scientists have identified mineral particles, calcium compounds, and various natural earth pigments, but the complete composition of the binding medium remains uncertain. Some researchers suggest modified lime wash, enhanced with organic additives such as plant gums, oils, or proteins. Others argue that multiple coating techniques evolved over several centuries as the city expanded. Without written construction records, no one knows the precise mixture, application sequence, or curing process that allowed these colors to adhere so effectively. Modern conservation laboratories can reproduce similar visual appearances, Yet none can confidently claim to recreate the exact ancient formula responsible for preserving pigment across 20 centuries. That unanswered question naturally leads to the limestone itself. Jerash was constructed mainly from locally quarried limestone and dolomitic limestone, rocks that modern engineers generally classify as relatively vulnerable compared with granite or basalt. Limestone dissolves slowly in weakly acidic rainwater, develops fractures through repeated heating and cooling cycles, and normally suffers progressive surface erosion over long periods. Northern Jordan experiences annual temperature variations exceeding 30 degrees Celsius between winter nights and summer afternoons, conditions that repeatedly expand and contract stone. By conventional geological expectations, countless architectural details should have disappeared long ago. Instead, many Corinthian capitals retain remarkably sharp carvings, decorative moldings remain recognizable, and hundreds of columns continue standing with minimal displacement, despite centuries of natural weathering. Detailed petrographic studies suggest that the outer surfaces of numerous blocks have become noticeably harder than the stone beneath them. Some scientists believe this resulted from natural recrystallization of calcium carbonate over long periods. Others suspect deliberate human intervention through protective mineral coatings that penetrated the limestone before hardening. Similar surface strengthening has been observed elsewhere in the Roman world, but Jerash presents an unusually widespread pattern that has never been fully explained. If craftsmen intentionally modified the stone after carving, they possessed practical knowledge of mineral chemistry that has never been completely reconstructed. The mystery deepens when examining the mortars that held the city together. Chemical analysis of surviving samples identifies lime as the primary ingredient, mixed with carefully graded sand, crushed ceramics in certain locations, and locally available mineral aggregates. However, the proportions vary considerably between monuments built during different construction phases. Unlike standardized modern cement, Roman builders often adjusted recipes according to structural requirements, moisture exposure, or foundation conditions. At Jerash, researchers have even detected occasional volcanic particles believed to have originated hundreds of kilometers away, suggesting that selected materials may have been transported over remarkable distances when superior performance was required. Exactly how these mixtures were proportioned remains uncertain because weathering has altered many surviving samples, leaving scientists unable to distinguish original chemistry from centuries of environmental change. Equally intriguing is the precision with which massive limestone blocks were assembled. Numerous walls display ashlar masonry, where stones fit so tightly that joints measure only a few millimeters. In many sections, mortar appears almost absent, yet the walls have remained stable despite repeated seismic activity. Roman surveyors certainly possessed sophisticated measuring instruments, but reproducing such consistency across an entire urban landscape required extraordinary control over quarrying, cutting, transportation, and finishing. Even slight inaccuracies would have accumulated across hundreds of meters of colonnades. Yet Jerash's principal streets remain remarkably straight, demonstrating construction tolerances impressive even by modern standards. The city's relationship with earthquakes provides another unresolved layer of the material mystery. Jerash lies close to the Dead Sea Transform Fault, one of the Middle East's major tectonic systems. Historical records describe devastating earthquakes, particularly those of AD 363 and AD 749, which damaged large portions of the city. Nevertheless, many columns remained standing while others collapsed in remarkably predictable patterns, suggesting that foundation behavior played a significant role. Excavations beneath several monuments reveal carefully prepared foundation layers composed of different grades of stone and compacted materials rather than simple bedrock placement. Some structural engineers argue these layered foundations distributed seismic forces more effectively than expected for ancient construction, though whether this was intentional design or empirical craftsmanship remains impossible to prove. Water engineering introduces another material puzzle. Jerash contained an extensive network of baths, fountains, underground drainage channels, and reservoirs supplied through sophisticated hydraulic systems. Many channels preserve waterproof linings that continue adhering firmly to masonry after centuries underground. Laboratory analysis indicates lime-based compositions enriched with fine mineral particles, yet no universal formula has emerged because different structures appear to use different mixtures. This variation suggests Roman engineers selected material recipes according to each structure's function, anticipating differences in water pressure, humidity, and long-term durability. Without surviving technical manuals specific to Jerash, the logic behind these adjustments remains largely speculative. The shifting sands of northwestern Libya, the Roman monuments of Sabratha, preserve a construction mystery that has survived nearly 2,000 years. Some of its buildings were carved from one of the region's softest local stones, yet they continue to stand only a few hundred meters from the Mediterranean, resisting salt, wind, and time in ways that still challenge modern material science. The ruins of Sabratha were never completely forgotten by local communities, but their true scale remained hidden for centuries beneath accumulated sand after the city's decline. Systematic archaeological excavations began in the early 20th century, particularly under Italian expeditions from the 1920s onward, gradually uncovering an extensive Roman city that once covered more than 40 hectares. Among the discoveries were the famous three-story theatre, temples, forums, baths, harbour structures, and hundreds of architectural fragments whose remarkable state of preservation immediately raised an important question. How had so many structures endured in one of the most destructive coastal environments on Earth, when many modern concrete and stone buildings begin to deteriorate within only decades? The first mystery begins with the stone itself. Much of Sabratha was constructed using locally available calcarenite, a marine sandstone composed largely of compressed shell fragments and calcium carbonate. Geological studies classify this material as relatively soft, with high porosity that normally allows moisture and dissolved salts to penetrate deep into the stone. Under ordinary conditions, such rock should weather rapidly along coastlines because seawater repeatedly enters microscopic pores before evaporating, leaving behind expanding salt crystals that gradually fracture the interior. Combined with strong Mediterranean winds carrying abrasive sand, seasonal humidity, and daily thermal expansion, the expected lifespan of finely carved architectural details should have been dramatically shorter than what is visible today. Yet visitors can still observe Corinthian capitals, decorative friezes, moldings, and carved inscriptions whose edges remain surprisingly crisp despite nearly 20 centuries of exposure. The durability appears inconsistent with the known mechanical properties of the stone itself, suggesting that the visible sandstone tells only part of the story. This contradiction has led researchers to examine whether Roman builders deliberately modified the stone after quarrying. Several conservation studies have identified evidence that portions of the exposed surfaces became chemically hardened over time, creating an outer layer significantly more resistant than the softer interior. The precise mechanism, however, remains uncertain. One possibility proposes that lime-rich coatings penetrated the surface before reacting with atmospheric carbon dioxide to form an artificial carbonate crust. Another suggests repeated applications of mineral-rich washes that slowly sealed the pore network. Others argue that naturally occurring marine aerosols interacted with construction materials over centuries to create an accidental protective shell. None of these explanations fully accounts for the remarkable consistency observed across different monuments throughout the site. Even microscopic analysis has yet to determine whether the hardened surface originated from deliberate engineering or from an exceptionally rare natural process that happened only under the environmental conditions surrounding ancient Sabratha. That uncertainty becomes even more intriguing when comparing weathered and protected portions of the same blocks. Freshly broken calcarenite remains noticeably softer than the exposed exterior, indicating that whatever transformed the surface penetrated only a limited depth. Modern conservation specialists have attempted to reproduce similar mineral crusts using synthetic consolidants, silica treatments, and calcium-based compounds, yet matching both the appearance and the long-term durability of the ancient surfaces has proven difficult. If Roman craftsmen intentionally engineered this effect, the exact preparation technique has disappeared entirely from the historical record. As the investigation moves beyond the stone itself, the mortar binding these monuments introduces another unresolved puzzle. Roman builders throughout the Mediterranean famously relied on lime mortar, but samples collected from Sabratha display unusually diverse internal structures. Some contain abundant, incompletely reacted lime fragments, while others appear remarkably homogeneous despite originating from neighboring buildings. Conventional construction theory would interpret these irregularities as evidence of inconsistent production. Recent research into Roman concrete, however, has challenged that assumption by suggesting that intentionally preserved lime clasts may have allowed ancient mortars to repair microscopic cracks through secondary chemical reactions whenever rainwater entered damaged areas. Whether Sabratha's builders intentionally exploited the same phenomenon remains unknown, because no surviving technical texts describe their manufacturing methods, firing temperatures, or mixing sequences. The coastal setting deepens the mystery even further. Sabratha lies directly beside the Mediterranean, where airborne chlorides continuously attack masonry. Modern reinforced concrete exposed to similar marine conditions frequently develops severe deterioration within decades, as salts accelerate internal damage and repeated wetting cycles weaken structural integrity. The Roman monuments, by contrast, have survived nearly 2 millennia despite repeated earthquakes, storms, coastal flooding, and prolonged abandonment. Although sections certainly collapsed through history, many standing walls, columns, foundations, and platforms remain structurally coherent, far beyond what their constituent materials would appear capable of achieving. This discrepancy suggests that the durability cannot be explained by stone quality alone, but instead reflects a broader understanding of material interaction that modern researchers are still attempting to reconstruct. Attention has therefore shifted toward the binders hidden inside foundations and harbor structures. Roman marine concrete has become famous because volcanic ash reacts with lime and seawater to produce exceptionally stable minerals such as aluminum-substituted tobermorite and philipsite, strengthening the material over time rather than weakening it. Yet Sabratha presents an important geographical complication. Libya possesses no major volcanic ash deposits comparable to those surrounding the Bay of Naples, traditionally considered the primary source of high-quality pozzolana used throughout the Roman Empire. If volcanic material was transported across more than 1,000 kilometers of Mediterranean trade routes, the enormous logistical investment demonstrates how valuable its engineering properties must have been. Alternatively, Roman builders may have identified local mineral mixtures capable of producing comparable hydraulic reactions, but convincing evidence for such substitutes has yet to emerge. Neither explanation has been conclusively verified, leaving the true composition of some construction materials unresolved. Archaeologists have also noted that many joints between large architectural blocks remain exceptionally tight despite centuries of structural movement. In several monuments, the mortar seams are so thin that they become almost invisible, making it difficult to determine whether extraordinary stone-cutting precision alone maintained stability or whether an equally sophisticated binding compound once occupied the microscopic gaps before gradually disappearing through weathering. Laboratory analysis continues to identify traces of carbonate phases and mineral inclusions, but no universally accepted reconstruction of the original mixture exists. Every new sample reveals subtle variations rather than a single standardized recipe, implying that Roman engineers may have adjusted formulations according to local stone, climate, and structural purpose, instead of relying on one universal material. At the heart of Rome, Italy, the Pantheon contains a building material that modern science still cannot fully reproduce. Nearly 2,000 years after its construction, the largest unreinforced concrete dome ever built continues to stand with remarkable stability, raising a question that has puzzled engineers for generations. What exactly did the Romans know about concrete that the modern world has yet to recover? The Pantheon seen today was most likely completed during the reign of Emperor Hadrian around AD 125, although it replaced an earlier temple commissioned by Marcus Agrippa. Despite remaining one of Rome's most famous landmarks throughout history, its true technological significance was only gradually revealed through scientific investigation during the 20th and 21st centuries. Archaeologists extracted concrete cores from different sections of the dome, geologists analyzed volcanic minerals under electron microscopes, and engineers created digital structural models capable of calculating stresses across the enormous shell. These studies transformed the Pantheon from an architectural masterpiece into one of history's greatest material science mysteries, because every new discovery answered one question while exposing several more. At first glance, the concrete appears surprisingly ordinary, consisting of lime, volcanic ash known as pozzolana, water, and stone aggregate. Yet detailed laboratory analysis revealed that its internal chemistry differs fundamentally from modern Portland cement. Instead of relying on industrial clinker, produced at temperatures approaching 1,450 degrees Celsius, Roman builders combined naturally occurring volcanic materials with lime in ways that produced exceptionally durable calcium-aluminum silicate hydrate minerals. Those minerals continued to evolve for centuries after construction, creating microscopic crystalline structures that strengthened rather than weakened the concrete over time. Modern concrete generally begins losing durability within decades when repeatedly exposed to moisture, salt, and temperature fluctuations. Yet the Pantheon's dome has endured earthquakes, seasonal expansion, pollution, and nearly 2 millennia of weathering while remaining largely intact. Scientists understand many of the chemical reactions involved, but the complete manufacturing process that allowed those reactions to occur remains frustratingly incomplete. As research advanced, an even more surprising discovery emerged from the concrete itself. White mineral fragments scattered throughout the Roman mixture had long been dismissed as evidence of poor workmanship or incompletely mixed lime. For decades, they were considered accidental impurities that skilled builders should have avoided. That interpretation changed dramatically when researchers began examining these fragments with high-resolution electron microscopy, X-ray diffraction, and elemental mapping. Instead of random defects, the particles appeared deliberately preserved inside the concrete, suggesting that Roman engineers intentionally followed a production method different from anything previously assumed. This realization led to what is now known as the hot mixing hypothesis, one of the most important breakthroughs in Roman concrete research. In studies published by researchers from the Massachusetts Institute of Technology and collaborators in 2023, evidence suggested that Roman builders may have mixed quicklime directly into the wet concrete before the material had fully hydrated. Such a process would generate intense heat through an exothermic chemical reaction, producing temperatures capable of altering mineral formation inside the mixture itself. The resulting lime clasts remained chemically active instead of becoming inert during production. When tiny cracks later formed and rainwater penetrated the concrete, those reactive lime particles dissolved, releasing calcium that combined with dissolved carbon dioxide to crystallize into calcium carbonate. Rather than allowing fractures to expand, the concrete effectively sealed many of its own microscopic cracks through natural chemical reactions. Laboratory experiments using reconstructed Roman-style mixtures demonstrated that artificially cracked samples containing hot mixed lime healed significantly more effectively than mixtures prepared using conventional methods. Yet despite this remarkable progress, fundamental questions remain unanswered. No surviving Roman text explains exactly how builders controlled the temperature, how long the mixture remained workable, how much quicklime was added, or whether different recipes existed for different structural components. Even if modern researchers understand the principle, the original manufacturing protocol that made it consistently successful has disappeared from history. The mystery deepens further when the dome itself is examined. Rising nearly 43.3 meters above the floor and spanning approximately the same distance across, the structure should have been far too heavy if built from a single uniform concrete. Instead, Roman builders gradually transformed the material as construction progressed upward. Dense travertine and heavier volcanic rock were used in the lower sections where compressive forces were greatest, while progressively lighter aggregates replaced them higher in the dome, until pumice, one of the lightest volcanic stones available, dominated the uppermost layers. Modern engineers recognize the brilliance of this weight reduction strategy, yet they still cannot determine precisely how Roman builders maintained seamless structural continuity while continuously changing aggregate composition. Concrete poured today often separates when mixtures vary significantly, but examinations of Pantheon core samples reveal gradual transitions rather than sharply defined layers. The changing density appears almost continuous, implying an extraordinary level of material control that has never been described in surviving historical records. Even more intriguing is the fact that the concrete was never intended to function as a passive material. Mineralogical studies reveal that reactions inside the dome continued for centuries after construction. New crystalline phases slowly developed as groundwater interacted with volcanic ash, while stable calcium-aluminum compounds formed intricate microscopic networks capable of resisting crack propagation. Unlike modern concrete, which generally becomes chemically less active with age, Roman concrete appears to have undergone a prolonged period of beneficial mineral evolution. Scientists have recreated portions of these reactions under laboratory conditions, but reproducing the complete sequence across hundreds of years remains impossible. Time itself may have acted as one of the essential ingredients, allowing chemical transformations that cannot simply be accelerated in modern experiments. Another unanswered question concerns the volcanic ash itself. Ancient writers referred broadly to pozzolana, obtained from the Bay of Naples, particularly around the Phlegraean fields, but recent geochemical analyses indicate that the Pantheon's concrete may not have relied upon a single uniform source. Trace element signatures vary between samples collected from different parts of the building, raising the possibility that Roman engineers deliberately selected specific volcanic deposits according to structural requirements. If true, this would suggest an advanced understanding of regional mineral properties centuries before geology emerged as a scientific discipline. However, no surviving supply records identify precisely where each shipment originated, leaving researchers unable to reconstruct the complete chain of material selection. The disappearance of this knowledge after the collapse of the Western Roman Empire makes the puzzle even more extraordinary. Medieval Europe continued constructing churches, castles, and cathedrals, yet none reproduced the Pantheon's massive unreinforced concrete dome. The sophisticated material technology that had allowed Roman engineers to manipulate volcanic chemistry, optimize aggregate density, and perhaps exploit hot mixing simply faded from practical use. Whether this resulted from the loss of skilled craftsmen, the collapse of industrial supply networks, or the disappearance of written technical manuals remains uncertain. By the time modern cement emerged in the 19th century, Roman concrete had become an archaeological curiosity rather than a living engineering tradition. On the northeastern edge of Egypt's Fayum oasis lies Karanis, an ancient city where thousands of ordinary mud brick buildings have survived for nearly 2,000 years, raising an extraordinary question. Were its builders using construction materials whose full composition has never been completely understood? Modern archaeology first identified the buried city in the late 19th century, but systematic excavation began in 1924 when the University of Michigan uncovered remarkably well-preserved streets, temples, granaries, workshops, and hundreds of houses emerging almost intact from beneath drifting desert sand. Founded during the reign of Ptolemy II Philadelphus around the 3rd century BC, and later flourishing under Roman rule, Karanis once supported a population estimated at between 3,000 and 5,000 inhabitants. While its papyri transformed historians' understanding of daily life in Roman Egypt, another mystery quietly emerged from the excavation itself. Nearly every surviving structure was built not from limestone or granite, but from sun-dried mud brick, a material modern engineers generally consider temporary. Yet across almost 20 centuries of extreme desert temperatures, seasonal groundwater fluctuations, and relentless sand-laden winds, entire neighborhoods remained standing far beyond the lifespan expected for unfired earth construction. The durability of these buildings has become increasingly difficult to explain through conventional assumptions alone. Traditional mud brick normally consists of Nile silt, clay, sand, and chopped straw, producing walls that require continuous maintenance because moisture, salt crystallization, and thermal expansion gradually weaken their internal structure. In most archaeological sites across North Africa and the Middle East, mud brick architecture eventually collapses into rounded mounds after centuries of exposure. Karanis behaves differently. Numerous houses still preserve staircases, storage rooms, wall niches, upper floor remains, and architectural layouts that remain easily recognizable today. While the exceptionally arid climate of the Fayum undoubtedly contributed to their survival, climate alone does not fully explain why so many structures retained such remarkable structural integrity. Scientific analyses of excavated bricks have revealed compositions that vary more than researchers initially expected. Instead of a uniform recipe, different districts appear to contain different proportions of clay minerals, quartz, calcium-rich particles, gypsum, soluble salts, and microscopic plant fibers. Some bricks exhibit compressive strengths noticeably greater than typical unfired mud brick, produced using reconstructed ancient techniques, suggesting that builders may have intentionally selected soils from different deposits or understood subtle combinations of mineral content that improved long-term performance. Whether these differences represent regional geological variation or a carefully controlled manufacturing process remains uncertain, because no ancient text describes exactly how the bricks were prepared. The greatest mystery, however, is found not inside the bricks themselves, but on their surfaces. Many walls were originally covered by a pale protective coating that has survived in fragments throughout the city. and in numerous locations this layer has become astonishingly hard, despite being only a few millimeters thick. At first glance, it resembles ordinary plaster, yet laboratory examinations indicate that its composition does not perfectly match conventional Egyptian gypsum plaster, Roman lime mortar, or the famous volcanic pozzolanic concrete used throughout the Roman Empire. Instead, the coating appears to contain a complex mixture of lime compounds, clay particles, naturally occurring salts, fine silicate minerals, and traces of organic substances whose precise function remains uncertain. Even more remarkable is the way this coating bonded with the underlying mud brick. Instead of separating from the wall after centuries of expansion and contraction, many surviving sections appear almost fused to the brick itself. Microscopic studies suggest that long-term chemical reactions may have gradually altered both the coating and the outer surface of the bricks, producing mineral phases that are denser and significantly more resistant to weathering than the original materials. Some conservation scientists have compared the process to a slow natural cementation, where dissolved minerals migrating through moisture repeatedly crystallized within microscopic pores, gradually transforming an initially soft plaster into something approaching the hardness of stone. Exactly how this transformation occurred, however, remains unresolved because the process unfolded over centuries under environmental conditions that cannot be perfectly recreated in laboratories. This raises another unanswered question. Was this extraordinary durability an intentional achievement or an accidental consequence of the Fayum environment? If ancient builders deliberately designed a coating capable of undergoing beneficial mineral transformation over time, they possessed an empirical understanding of material behavior far beyond what surviving written records reveal. If, on the other hand, the hardening resulted entirely from natural geochemical processes, researchers still struggle to explain why similar transformations are not consistently observed at other mud brick settlements exposed to comparable climates throughout Egypt. The mystery deepens when groundwater chemistry is taken into account. Fayum is characterized by fluctuating water tables and relatively high concentrations of dissolved salts, conditions that usually accelerate the destruction of earthen architecture. Salt crystals expand within microscopic pores, producing internal stresses that fracture bricks from the inside. This mechanism is responsible for severe deterioration at countless archaeological sites worldwide. Yet many buildings at Karanis exhibit only surface erosion rather than catastrophic structural failure. One possibility is that the protective coating altered the movement of moisture through the walls, reducing destructive salt crystallization within the bricks themselves. Another hypothesis proposes that the pore structure created by the original brick mixture allowed salts to migrate harmlessly toward exterior surfaces instead of accumulating deep within the masonry. Neither explanation has been conclusively demonstrated. Researchers have also noticed that the internal microstructure of many Karanis bricks contains networks of extremely fine air voids distributed throughout the material. These microscopic cavities likely improved thermal insulation, helping buildings remain relatively cool during scorching desert days, while slowing heat loss after sunset, when temperatures in the Fayum can fall dramatically. Such thermal stability would have reduced repeated expansion and contraction, indirectly increasing structural longevity. Whether ancient builders intentionally engineered this porous structure through careful control of moisture content, fiber proportions, or drying conditions remains unknown, because reconstructed bricks rarely reproduce the same microscopic characteristics found in archaeological samples. Organic reinforcement presents another puzzle. Straw, reed fragments, and other plant fibers are common ingredients in ancient mud brick because they reduce shrinkage during drying. Normally, these organic components decay over time, leaving internal voids that weaken the structure. In Karanis, however, Microscopic examinations have shown that some fibers retain recognizable form despite their great age. Researchers suspect that gradual mineral replacement may have partially preserved these organic materials, with dissolved calcium and silica occupying spaces once filled by biological tissue. Similar mineralization occurs in certain fossilization processes, but why it appears so effectively within construction materials at Karanis is still poorly understood. What makes the city especially important is that none of these observations alone fully explains its preservation. The bricks are unusual, but not unprecedented. The plaster is chemically distinctive, but not entirely unique. The desert climate is favorable, but cannot account for every surviving wall. Instead, the evidence suggests that several independent factors may have interacted over centuries, producing a construction system whose long-term performance exceeded the expectations of both ancient builders and modern scientists. Every new laboratory analysis reveals another layer of complexity, while leaving the original manufacturing knowledge frustratingly incomplete.
Sera is a tiny island in the Gulf of Mirabello off the northeastern coast of Crete. Barely visible on most maps and measuring only a few square kilometers, it seems an unlikely place for one of the most sophisticated maritime communities of the Bronze Age. Yet beneath its rocky hills lies evidence of a civilization whose engineering, trade networks, and urban planning continue to challenge archaeologists today. The site was first identified in the late 19th century and later excavated extensively by archaeologists seeking to understand the wider world of Minoan Crete. What they uncovered was unexpected. Instead of a simple fishing settlement, Sera revealed itself as a thriving harbour town occupied primarily between roughly 1900 and 1450 BCE. Streets, workshops, storage facilities, elite residences, and imported goods emerged from the soil, suggesting a level of economic complexity far beyond what most would expect from a small island with limited resources. The discovery immediately raised a fundamental question. How did such an isolated and environmentally constrained location become an important node within one of the most advanced civilizations of the ancient Mediterranean? The first mystery begins with survival itself. Sera is a dry island. Unlike major settlements situated near rivers, springs, or fertile plains, the inhabitants of Sera lived in an environment where fresh water was scarce and agricultural land was limited. Modern surveys indicate that annual rainfall in eastern Crete is relatively low compared with many other Mediterranean regions. Yet archaeological evidence suggests that hundreds, perhaps thousands of people occupied the settlement during its peak. Storage installations, domestic architecture, and industrial facilities all indicate long-term habitation rather than temporary seasonal occupation. The challenge is difficult to overstate. Every litre of water had to be collected, stored, protected, and distributed. Excavations revealed sophisticated systems of cisterns, channels, and collection surfaces integrated directly into the architecture of the town. Rainwater harvesting appears to have been practiced on a scale remarkable for the period. Roofs, courtyards, and paved surfaces were carefully designed to direct runoff towards storage facilities. Some researchers have compared the efficiency of these systems to later water management strategies used in arid regions of the Roman Empire. Yet no written engineering manuals survive to explain how these designs were calculated. The result suggests a practical understanding of hydrology that remains largely invisible in the archaeological record. Equally intriguing is the layout of the settlement itself. When the site was mapped in detail, archaeologists noticed that many of the streets followed logical routes optimized for movement across steep terrain. The arrangement does not appear entirely random, nor does it resemble the uncontrolled growth typical of many early settlements. Instead, certain sectors display evidence of planning. Pathways connect storage areas to harbour facilities. Residential districts occupy advantageous elevations. Drainage routes appear integrated into the urban fabric. Such planning raises difficult questions about measurement and surveying during the Bronze Age. Modern engineers rely on precise instruments to calculate gradients and optimize infrastructure. The inhabitants of Ceara possessed no known compasses, levels, or advanced surveying equipment. Nevertheless, they successfully constructed a settlement capable of functioning efficiently within a challenging landscape. Similar patterns are observed at larger Minoan centres such as Knossos and Malia, suggesting that urban planning may have been a more advanced discipline within Minoan society than previously assumed. The architecture presents another puzzle. Crete lies within one of the most seismically active regions of the Mediterranean. Geological studies indicate that major earthquakes have repeatedly struck the island throughout history. Ancient settlements faced constant danger from seismic activity. Yet many structures at Ceara survived long enough to undergo renovation, expansion, and continuous occupation across generations. Detailed examination of surviving walls reveals construction techniques that appear surprisingly resilient. Builders frequently employed composite masonry systems consisting of larger outer stones combined with smaller infill material. The resulting structures were not rigid monoliths, but flexible assemblies capable of dissipating stress. Some engineers have suggested that these methods may have unintentionally provided a degree of earthquake resistance. While not equivalent to modern seismic engineering, the approach demonstrates a practical understanding of structural behavior gained through centuries of experience. Similar adaptive techniques can be observed at other Minoan sites, hinting at a broader tradition of construction knowledge that was never formally recorded. The industrial evidence from Ceara deepens the mystery. Excavations uncovered workshops associated with pottery production, storage, processing activities, and various crafts. Specialized production requires organization, labor management, and supply chains. Raw materials needed to be imported or transported. Finished goods required distribution. Such activities imply the existence of administrative systems capable of coordinating complex economic operations. Yet unlike modern societies, the Minoans left behind few easily decipherable records. Their script, known as Linear A, remains undeciphered despite decades of research. Archaeologists know that records existed. Clay tablets and inscriptions confirm that information was being stored and transmitted. However, the actual content remains inaccessible. It is as though historians discovered a modern corporation's archives but lost the key required to read every document. Consequently, the mechanisms that govern production, taxation, inventory management, and trade remain among the greatest unresolved mysteries of Bronze Age archaeology. Nothing, however, is more astonishing than the evidence for maritime trade. This is where the story of Ceara becomes truly extraordinary. Archaeological analysis has identified imported materials and artifacts originating from multiple regions of the Eastern Mediterranean. Pottery styles connect the settlement to other parts of Crete, the Cycladic Islands, and distant coastal communities. Scientific studies of ceramic composition indicate movement of goods across hundreds of kilometers of open water. Exotic materials likely traveled through networks extending toward the Levant and Egypt. For a small island settlement, the scale of connectivity is remarkable. Bronze Age sailors lacked magnetic compasses. They possessed no sextants, chronometers, or accurate nautical charts. GPS would remain unimaginable for another 3.5 millennia, yet Minoan ships routinely crossed the Aegean Sea, one of the most geographically complex maritime environments in the world. The Aegean contains thousands of islands, unpredictable winds, seasonal weather shifts, and powerful currents. Successful navigation required extraordinary precision. a vessel drifting only a few degrees off course could miss its destination entirely. Nevertheless, trade networks operated consistently enough to support specialized economies and sustained cultural exchange across vast distances. How was such navigation achieved? One theory suggests that Minoan sailors developed an accumulated body of environmental knowledge rivaling modern indigenous navigation traditions. Mariners may have memorized seasonal wind patterns, observed cloud formations, tracked wave behavior, and used celestial bodies as navigational references. Some researchers compare these possibilities to the sophisticated non-instrument navigation practiced by Polynesian voyagers, who crossed thousands of kilometers of Pacific Ocean using stars, swells, birds, and environmental cues. The comparison is striking. Polynesian navigators operated without modern instruments, yet successfully reached islands separated by enormous distances. If similar observational systems existed among Minoan sailors, they may explain how settlements like Sierra remained integrated into a vast maritime network. The problem is that direct evidence for these navigational methods has almost entirely vanished. Knowledge transmitted orally leaves few traces in the archaeological record. But what do you think? Was Sierra's success simply the result of centuries of accumulated experience? Or did the Minoans possess navigational and engineering knowledge far more advanced than we currently understand? Share your thoughts in the comments below. Coastal city slowly lost the sea, yet refused to collapse. Settlement built on unstable ground still stood for over a millennium. And beneath it all, a water system that should not have worked, yet did. Histria is not just an ancient ruin. It is a contradiction preserved in stone. Founded in the 7th century BCE by settlers from Miletus, Histria became the earliest Greek colony on the western coast of the Black Sea, and when systematic archaeological excavations began in the early 20th century, they revealed a continuous sequence of occupation lasting over 1,000 years, with each layer uncovering fortifications, temples, and hydraulic systems, while at the same time intensifying a central mystery: how a city could survive in environmental conditions that should have made long-term habitation unsustainable. Histria was originally established directly along the Black Sea coastline, but geological evidence shows that sediment carried by the Danube River gradually pushed the shoreline outward over centuries, transforming the coastal landscape so dramatically that today the ruins lie several kilometers inland, separated from open water by lagoon systems. This was not a minor shift, as studies estimate a displacement of approximately 5 to 7 kilometers over 2,000 years, a change that should have effectively destroyed any port-dependent economy. Yet, archaeological findings reveal continued occupation and economic activity long after this transformation, with imported amphorae, coinage, and ceramics still appearing in later layers, suggesting that trade networks remained functional despite the loss of direct maritime access, raising a critical, unresolved question: how did Histria sustain its role in regional exchange without a port? Some theories propose the existence of artificial canals or seasonal navigation routes through the lagoons, but unlike well-documented harbour systems such as those of Alexandria, no large-scale infrastructure has been definitively identified, leaving the mechanism of adaptation largely invisible. The city was constructed on soft, alluvial soil, a substrate highly prone to subsidence and instability, which modern engineering would classify as unsuitable for long-term structural development. Yet despite this, Histria's defensive walls, public buildings, and sacred structures endured for centuries, with excavations revealing layered foundations composed of alternating materials that appear to distribute load and reduce localized stress, a technique that closely resembles modern principles of load dispersion and ground stabilization. even though there is no textual evidence that ancient builders possessed formalized knowledge of such geotechnical methods. In contrast, cities like Pompeii were built on relatively stable volcanic terrain, minimizing the need for complex foundational adaptations, which makes Histria's persistence even more striking, leading to a fundamental question. Was this engineering knowledge developed purely through empirical trial and error, or does it reflect a broader, systematized understanding that has not survived in written form? The most perplexing aspect of Histria lies beneath its surface in its water systems, as the city occupied a transitional zone where freshwater inflow from inland sources met marine intrusion from the Black Sea, creating fluctuating salinity conditions that would typically contaminate groundwater and render stable freshwater access extremely difficult. In modern hydrogeology, maintaining potable water in such an environment requires detailed knowledge of aquifer dynamics, pressure gradients, and permeability. Yet archaeological evidence shows that Histria achieved precisely this, with excavations uncovering deep wells that consistently yielded fresh water, even in close proximity to saline lagoon systems, some extending several meters below the surface, indicating deliberate targeting of confined aquifers trapped beneath impermeable sediment layers, while additional findings suggest the presence of organized water channels and storage structures, pointing toward planned water management rather than opportunistic use. The contradiction becomes more pronounced when considering that in coastal environments, freshwater typically forms a thin lens floating above denser saltwater, a fragile system easily disrupted by over-extraction or environmental change, and according to modern models, sustaining such a lens over long periods requires careful control and understanding of recharge rates. Yet Histria's system appears to have functioned for centuries without clear evidence of advanced filtration or monitoring infrastructure. Comparisons can be made to the Qanat systems of ancient Persia, which demonstrate sophisticated underground water extraction, but those systems operated in more stable geological conditions and are well documented, whereas Histria's environment was far more unpredictable and its methods remain undocumented. The absence of clear filtration systems further deepens the mystery, as there is no definitive evidence of advanced purification technology, raising the question of how salinization was avoided, with possible explanations including precise placement of wells in zones where freshwater pressure exceeded saline intrusion, seasonal regulation of water extraction, or the use of natural geological barriers that were understood intuitively but never formally recorded. Yet all of these remain speculative, because the central paradox persists. The system worked, but the mechanism behind its long-term reliability is still not fully understood. Urban development typically follows a recognizable pattern of gradual evolution, with cities expanding incrementally, adapting infrastructure over time, and refining layouts through successive phases. But at Histria, certain sectors appear to have been constructed with a level of organization that suggests prior planning rather than organic growth, as street grids, drainage systems, and building alignments display coherence and intentionality from relatively early stages, a pattern that contrasts with cities like Miletus, where urban planning became more structured only after extended development, creating an anomaly in which Histria seems to behave as though it was designed with a degree of foresight that would normally require generations of accumulated knowledge, raising the question of whether this reflects an accelerated learning process or the application of pre-existing planning principles that have not been preserved in historical records. Unlike cities that ended abruptly due to catastrophic events such as volcanic eruptions, invasions, or earthquakes, Histria's decline appears to have been gradual, with no definitive destruction layer, no widespread evidence of burning, and no clear signs of violent abandonment, instead showing a slow loss of function over time likely influenced by environmental changes such as the expansion of lagoon systems and the shifting of trade routes, which reduced the city's strategic importance. However, this leads to a deeper paradox. As a settlement that demonstrated the ability to adapt to unstable ground, shifting coastlines, and complex hydrological conditions, ultimately failed to adjust to long-term environmental transformation, raising the unresolved question: why did a system capable of solving immediate and highly complex challenges prove incapable of sustaining itself against gradual, predictable change? Do you think these systems were the result of accumulated experience or traces of a lost knowledge? Share your thoughts in the comments below. Colonna is a low hill rising from the northwestern coast of Aegina Island in Greece, barely visible above the blue waters of the Saronic Gulf. At first glance, it seems insignificant compared with the palaces of Crete, the citadels of Mycenae, or the legendary ruins of Troy. Yet beneath this modest mound lies one of the most perplexing technological stories of the ancient Aegean. For more than 7,000 years, people repeatedly built, rebuilt, and transformed this settlement. Long before the emergence of classical Greece, long before the Parthenon, and even before the great Minoan palaces reached their peak, Colonna appears to have become a center of engineering, metallurgy, maritime trade, and urban planning whose sophistication continues to challenge conventional explanations. The site first attracted scholarly attention in the 19th century, when travelers noticed unusual ancient remains scattered across the hill. Systematic excavations began in the early 20th century under German and Austrian archaeologists, revealing an extraordinary sequence of occupation layers stretching from the Neolithic period around 5000 BC through the Bronze Age. Excavators eventually identified more than 10 major settlement phases stacked one above another. Few sites in the Aegean preserve such a continuous record of technological and social development. Every new layer seemed to reveal another surprise, suggesting that Colonna was not merely a village but one of the most influential centers in the prehistoric Eastern Mediterranean. The first mystery emerges from the scale of construction itself. During the early Bronze Age, around 2500–2300 BC, most communities in the Aegean consisted of relatively small settlements with modest architecture. Yet at Colonna, archaeologists uncovered a massive structure known as the White House. Despite its modern nickname, the building bears no relation to the famous American landmark. What astonished researchers was its complexity. The structure contained multiple rooms, thick stone walls, carefully organized storage areas, and a layout that suggests centralized administration. The building occupied a dominant position within the settlement and required enormous labor investment. Comparisons reveal why this discovery is so puzzling. The White House predates many of the monumental architectural achievements traditionally associated with the Minoan civilization on Crete. At a time when much of the region was still organized into small agricultural communities, Colonna appears to have constructed something approaching a proto-palatial building. Archaeologists examining its foundations discovered evidence of deliberate structural planning. Large stones were selected and arranged in ways that distributed weight efficiently. The walls were not random accumulations of rubble but carefully engineered systems designed for stability. The builders seem to have possessed practical knowledge of load-bearing architecture centuries before such concepts appear in written historical records. The mystery deepens when examining Colonna's fortifications. Around the late 3rd millennium BC, the settlement became protected by massive defensive walls. Some sections reached thicknesses of approximately 4 to 5 meters. Multiple defensive circuits surrounded key areas of the site, creating a layered security system uncommon for the period. Strategic angles improve visibility and increase defensive effectiveness. Such planning implies not only architectural expertise, but also advanced understanding of military engineering. This presents an important historical problem. Comparable settlements throughout the Cyclades often lacked major fortifications. Many mainland Greek communities of the same period possessed little evidence of large-scale defensive construction. Why would a relatively small island settlement invest such immense resources into military architecture? One possibility is that the Aegean world was experiencing levels of maritime competition and conflict far greater than previously assumed. If true, Colonna may preserve evidence of an entire geopolitical landscape that has largely disappeared from the archaeological record. Its location offers another clue. Aegina occupies a strategic position between mainland Greece, the Peloponnese, the Cycladic Islands, and Crete. Modern shipping routes still recognize the importance of this region. Scientific analyses of materials recovered from Colonna reveal extensive trade connections. Obsidian originated from Melos, hundreds of kilometers away. Copper arrived from multiple sources. Pottery styles demonstrate interaction with distant communities across the Aegean. Such evidence indicates participation in a vast maritime network long before the rise of the famous Bronze Age kingdoms. The technological implications are profound. Moving significant quantities of stone, metals, and finished goods across open water required reliable vessels, navigational knowledge, and organizational systems capable of coordinating long-distance exchange. Yet, direct evidence remains frustratingly scarce. Wooden ships rarely survive for millennia beneath Mediterranean conditions. Archaeologists can observe the products of maritime technology, but possess very little of the technology itself. The result is a strange historical paradox. We know extensive sea trade existed because the artifacts prove it, but we still do not fully understand the vessels and navigational methods that made such trade possible. Among all of Colonna's enigmas, however, none is more significant than its role as a metallurgical center. This is where the site becomes truly extraordinary. During the early Bronze Age, copper represented one of humanity's most transformative technologies. Producing useful metal was not a simple task. Ore had to be identified, extracted, transported, crushed, heated, and refined under carefully controlled conditions. Even small variations in temperature or airflow could determine whether a smelting operation succeeded or failed. Excavations at Colonna have uncovered evidence suggesting intensive metallurgical activity. Scientific analyses of copper artifacts indicate connections with multiple ore sources. Chemical signatures reveal complex supply networks extending beyond the island itself. Researchers have also identified remains associated with metal production, including slag and traces of high-temperature industrial processes. The evidence suggests that Colonna was not merely consuming imported metals, but actively participating in transformation and manufacturing. The technological challenge involved should not be underestimated. Copper melts at approximately 1085 degrees Celsius. Achieving and maintaining such temperatures requires sophisticated furnace design and careful management of oxygen flow. Experimental archaeology has demonstrated that successful prehistoric smelting depends on remarkably precise control of combustion conditions. Yet the people of Colonna appear to have mastered these processes more than 4,000 years ago. This raises a fundamental question. How did a relatively small island community acquire such expertise? Some scholars argue that technological knowledge spread through extensive exchange networks, linking the Aegean with Anatolia and the Near East. Others suggest that local experimentation played a larger role. Neither explanation fully resolves the mystery. The archaeological record demonstrates the presence of advanced metallurgical capabilities, but the pathways through which that knowledge developed remain unclear. The scale of metalworking also implies broader organizational complexity. Metallurgy requires specialists, specialists require food surpluses require efficient economic systems. In other words, copper production at Kelowna may indicate a society far more structured than archaeologists once imagined. The settlement begins to resemble an industrial and commercial hub, rather than a simple island village. Another mystery emerges from the site's remarkable continuity. Over thousands of years, successive generations repeatedly built upon earlier foundations. Excavators have documented more than 10 major settlement levels. New buildings often occupied exactly the same locations as older structures. This pattern suggests more than convenience. It implies transmission of technical knowledge across centuries. Builders appear to have understood which areas provided stable foundations and favorable conditions for construction. Maintaining such knowledge without extensive written records presents a fascinating puzzle. Modern engineering relies on documentation, plans, and mathematical calculations. Prehistoric societies depended on oral transmission and practical experience. Yet Kelowna's inhabitants managed to preserve architectural traditions across enormous spans of time. The consistency visible in the archaeological layers suggests a continuity of expertise that remains difficult to explain. The name Kelowna comes from a solitary column that once stood on the hill. Although the surviving column belongs to a later temple, the settlement's elevated location may have served as a landmark for sailors in the Saronic Gulf. Some researchers suggest Kelowna was not only a settlement but also an important maritime reference point, reflecting its long connection to the sea. Stone is supposed to resist human intention. It fractures, it erodes, it forces compromise. Yet in the high plateau of northern Spain, there exists a place where stone does the opposite, it obeys. Entire homes, stairways, corridors, and hydraulic systems are not built on the land, but carved into it with a level of control that appears strangely deliberate. At Tiames, the question is not simply who built it, but how such precision emerged without leaving behind the process that should have created it. Tiames was known locally for centuries as a ruin embedded in rock, but systematic archaeological study began in the late 19th and early 20th centuries, with major excavations conducted under Spanish archaeologist Blas Tarracina in the 1920s and 30s. These investigations revealed a settlement with origins traced to the Celtiberians around the 5th century BCE, later expanded under Roman occupation. Excavations uncovered carved residential complexes, a Roman forum, thermal baths, and an extensive network of subterranean structures, all integrated directly into red sandstone bedrock, transforming what initially appeared to be natural erosion into clear evidence of a deliberately engineered urban system. Unlike cities such as Pompeii or Machu Picchu, where materials are assembled layer by layer, Tiames follows an inverse architectural logic, in which space is created by removing matter rather than adding it. Archaeological mapping demonstrates that large portions of the settlement were carved downward and inward from continuous sandstone formations, a method that requires absolute commitment because every cut is irreversible and every error permanent. Yet within Tiames, there are no clear signs of large-scale correction, no abandoned chambers, no misaligned corridors, and no evidence of progressive trial and error. Instead, the spatial organization appears intentional from the outset, with residential rooms typically ranging between 8 and 15 square meters and staircases, maintaining consistent riser heights of approximately 15 to 20 centimeters. This level of uniformity implies not only technical capability but also pre-visualization. suggesting that builders possess the ability to mentally construct and plan complex three-dimensional layouts before executing them directly into stone. Sandstone, the dominant geological material at TMS, typically measures between 6 and 7 on the Mohs hardness scale, making it significantly softer than granite and therefore workable with iron tools available during later occupation phases. However, the central issue is not whether the stone could be cut, but how it was cut with such remarkable consistency across large surfaces. Detailed analysis of surviving walls reveals flat planes extending several meters with minimal deviation, parallel tool marks that maintain consistent spacing, and sharply defined internal angles approaching 90 degrees features that imply controlled repetitive motion rather than irregular manual shaping. Experimental archaeology indicates that achieving such precision manually would require not only extensive labor, but also standardized techniques, including consistent tool angles, force application, and measurement systems maintained across time. When compared to Petra, where Nabatean rock-cut architecture visibly preserves irregularities, asymmetries, and layered carving stages, TMS appears unusually restrained and uniform, suggesting a different operational approach. Even more striking are the staircases, where measurements across multiple excavation zones reveal variations in step height, often remaining within less than 1 centimeter, a tolerance level that implies either a formalized measurement system or an exceptionally disciplined transmission of craftsmanship across generations. Yet no written documentation survives to describe such systems among the Celtiberians, and although Roman engineering could theoretically account for refinement, stratigraphic evidence confirms that some of the most precise carvings predate full Roman integration, creating a persistent gap between expected technological capability and the physical evidence preserved in stone. Beneath the visible structures of TMS lies a secondary system composed of channels, reservoirs, and conduits carved directly into the bedrock, forming a network that appears neither random nor purely opportunistic. Gradient analysis conducted on preserved water channels demonstrates slopes calibrated with notable consistency, allowing water to flow efficiently without stagnation or destructive erosion, with some inclines maintained steadily across distances exceeding 20 meters. Such precision suggests an applied understanding of fluid behavior, not in abstract theoretical terms, but through repeatable and controlled engineering practice. Comparable hydraulic strategies are documented at Petra, where water collection and distribution systems were essential for survival in arid conditions. Yet TMS presents a more enigmatic case because it exists in a region where water resources are limited and less predictably available. This creates a paradox. The infrastructure reflects a level of planning appropriate for sustained habitation, yet the surrounding environment does not clearly justify such investment, raising the possibility that TMS functioned within a broader, now lost system of resource management or regional interaction. TMS occupies an elevated plateau within the modern province of Soria, characterized by a dry climate, seasonal temperature extremes, and relatively poor agricultural conditions. From a conventional economic or settlement perspective, such a location would not be considered optimal for supporting a large and stable population. Nevertheless, archaeological estimates suggest that during its peak, TMS may have sustained anywhere from several hundred to over 1,000 inhabitants, implying the existence of reliable strategies for water management, food acquisition, and long-term habitation. The carved nature of its architecture may have provided passive thermal regulation, with interior spaces maintaining more stable temperatures than the external environment, representing a sophisticated adaptation to climatic stress. However, what remains difficult to reconcile is the apparent completeness of this adaptation. as there is little evidence of gradual development or incremental improvement, suggesting instead that these solutions appeared already refined at the time they were implemented. In contrast to sites such as Pompeii, where sudden catastrophic events preserved a clear narrative of destruction, TMS offers no equivalent archaeological signature of abrupt collapse. There are no extensive burn layers, no widespread structural failures, and no mass burial evidence that would indicate a singular crisis event. Instead, the material record points toward a gradual process of depopulation, with artifacts becoming increasingly scarce and signs of maintenance diminishing over time until the settlement was ultimately abandoned. This absence of a defined endpoint complicates interpretation, as it removes the possibility of attributing the city's disappearance to a single identifiable cause, leaving open multiple possibilities ranging from economic shifts to environmental pressures or broader socio-political changes. If a city can exist with this level of precision, yet leave behind no trace of how it was created, what do you think we are missing in our understanding of ancient technology? Share your thoughts in the comments below. Located in the Zaravshan Valley of present-day Tajikistan near the border with Uzbekistan, Sarazm is one of the most remarkable prehistoric settlements ever discovered in Central Asia. More than 5,500 years ago, this community emerged in a region once considered far removed from the world's earliest centers of civilization. Yet beneath its dusty plains lies evidence of a society whose technological achievements continue to surprise archaeologists. Long before the Silk Road connected Asia, before the rise of the great Persian empires, and while the first cities of Mesopotamia were still taking shape, Sarazm had already developed into a thriving center of metallurgy, trade, architecture, and specialized production. The more researchers uncover about the site, the more puzzling it becomes that such a sophisticated society could have flourished so early and so far from the traditional heartlands of ancient civilization. The story of Sarazm's discovery began in 1976, when local farmer Ashurali Taylornoff noticed unusual stone tools while working the land. Archaeologists soon realized that they had uncovered one of Central Asia's most important prehistoric sites. Excavations eventually revealed a settlement covering approximately 90 to 100 hectares, making it one of the largest proto-urban centers in the region. Radiocarbon dating placed its occupation between roughly 3,500 and 2000 BCE. This means Sarazm flourished during the same period as the Uruk cities of Mesopotamia, and centuries before many societies in Central Asia were thought capable of supporting complex urban life. What immediately puzzled researchers was the scale of organization visible throughout the settlement. Sarazm was not a simple farming village. Excavations revealed residential quarters, production zones, storage areas, workshops, ceremonial spaces, and evidence of social differentiation. Such complexity is normally associated with large river civilizations possessing centralized administrations. Yet Sarazm developed in a semi-arid environment surrounded by mountains. Unlike Mesopotamia, there is no evidence for a powerful state bureaucracy directing construction or controlling resources. Nevertheless, the settlement appears to have functioned as a regional hub for centuries. How a community in this location accumulated enough wealth, labor, and technical knowledge to sustain such a settlement remains one of the site's greatest mysteries. The most remarkable puzzle revolves around metallurgy. Among all discoveries at Sarazm, none have generated more debate than the evidence for advanced copper production. Archaeologists uncovered furnaces, crucibles, molds, slag deposits, and specialized workshop areas indicating large-scale metalworking activity. These finds demonstrate that metallurgy was not a minor craft practiced by a few individuals. It was a central component of the settlement's economy. The technological implications are extraordinary. Producing usable copper is far more difficult than simply collecting metal-bearing rocks. Copper ores must first be identified, extracted, crushed, sorted, heated, and smelted at temperatures often exceeding 1,000 degrees Celsius. Maintaining such temperatures requires controlled airflow, carefully selected fuels, and extensive practical knowledge accumulated through generations of experimentation. Even small errors can ruin an entire batch of metal. Yet Sarazm's metalworkers consistently produce tools, ornaments, and weapons of impressive quality. Even more intriguing is the fact that many artifacts were not made from pure copper. Scientific analyses have revealed arsenical copper, leaded copper, and early alloy compositions. This suggests metallurgists understood that altering the chemical composition of metal could improve hardness, durability, or casting properties. Such knowledge resembles the experimental foundations that would eventually lead to the Bronze Age. The mystery is not that these people used metal. The mystery is how they acquired such sophisticated metallurgical expertise so early and so far from the major centers traditionally associated with technological innovation. Researchers continue to debate whether these alloy compositions were intentional. Some scholars argue that naturally occurring ore mixtures may explain the chemical signatures. Others point out that repeated consistency across artifacts suggests deliberate control. If intentional, Sarazm's metalworkers possessed an understanding of material properties that remains difficult to reconstruct. They left no written manuals, no technical diagrams, and no records explaining their methods. Their knowledge vanished while the product survived. Another unresolved question concerns the source of the raw materials. Isotopic analyses indicate that the copper used at Sarazm originated from multiple mining regions. Some sources appear linked to the Zaravshan Mountains, while others may trace back toward Afghanistan and neighboring highland zones. Transporting heavy ore across rugged terrain would have required substantial logistical organization. Yet there is no evidence of roads, wheeled transport systems on a large scale, or centralized governments coordinating such operations. Somehow, thousands of kilograms of raw material moved through some of the most challenging landscapes in Central Asia. The mystery deepens when examining the site's trade connections. Excavations have uncovered lapis lazuli from Afghanistan, turquoise from distant mining regions, marine shells originating hundreds of kilometers away, and carnelian beads associated with exchange networks extending toward the Indus Valley. These discoveries reveal a commercial system operating on a scale once thought impossible for the period. Some artifacts traveled distances exceeding 1,000 kilometers before arriving at Sarazm. To appreciate the significance of this network, consider that many later Bronze Age societies maintained trade routes of comparable length, only with the support of organized states and administrative institutions. Sarazm appears to have participated in similarly extensive exchange systems centuries earlier. Who coordinated these connections remains unknown. Were there professional merchants crossing mountains and deserts? Tribal alliances? Seasonal caravans? Archaeology has not yet provided a definitive answer. The settlement's architecture introduces another layer of uncertainty. Excavations reveal substantial mud brick structures, large rectangular buildings, courtyards, and carefully organized activity zones. Certain layouts repeat throughout the site, suggesting that builders followed shared planning principles. Some structures contain walls exceeding 1 meter in thickness. Others display evidence of repeated renovation while maintaining similar geometric proportions. Such patterns imply the existence of construction knowledge passed between generations, yet Sarazm predates any known writing system in the region. Without written plans, how were architectural standards preserved across centuries? Some researchers propose the use of standardized measurements or practical geometric techniques. Others argue that skilled builders transmitted knowledge through apprenticeship systems. Whatever the mechanism, the consistency visible across the settlement suggests a level of engineering coordination rarely associated with prehistoric communities. Environmental adaptation presents another fascinating puzzle. Sarasm existed in a region vulnerable to climatic fluctuations, seasonal water variation, and seismic activity. Despite these challenges, the settlement survived for more than a millennium. Archaeological evidence suggests inhabitants managed water resources effectively and developed construction techniques capable of withstanding environmental stress. Some foundation designs incorporate layered materials that may have improved structural stability. Whether these features represent intentional engineering solutions or accumulated practical experience remains uncertain. Equally mysterious is the degree of labor specialization visible across the site. Excavators identified concentrations of beads, metalworking debris, pottery production waste, and stone tool manufacturing in separate zones. This pattern indicates that different groups focused on specific crafts. Such specialization is a hallmark of complex economies because it requires reliable food production capable of supporting non-farming populations. Comparisons with contemporary settlements make Sarasm even more unusual. Many villages of the 4th millennium BCE consisted primarily of agricultural households, producing most necessities locally. Sarasm, by contrast, exhibits evidence of artisans dedicated to metallurgy, bead-making, ceramics, and long-distance exchange. The economic structure resembles an emerging urban centre rather than an isolated village. Then, after nearly 15 centuries of prosperity, Sarasm declined. Around 2000 BCE, occupation decreased dramatically. No signs of catastrophic warfare have been discovered. No evidence points to a single destructive event. Instead, the settlement appears to have faded gradually. Climate change, shifting river systems, resource depletion, and the reorganization of trade routes have all been proposed as explanations. None fully account for the disappearance of such an influential center. History usually moves forward. It builds, peaks, declines, and disappears, leaving behind a clear direction like a line drawn across time. But there are places where that line does not behave as expected, places where it fractures, bends back on itself and repeats. Dinargetia is one of those places, not because of a single extraordinary event, but because of something far more unsettling. It was never meant to be a one-time city. It was returned to, again and again, across centuries, by completely different civilizations that should have had no reason to follow the same choice so precisely. On the edge of the Danube, where the river slows and widens before pushing toward the Black Sea, the remains of Dinargetia sit quietly, almost unremarkable at first glance. Low stone walls, broken foundations, scattered outlines of buildings that no longer exist. Nothing about it suggests inevitability. Nothing about it appears unique enough to explain why it mattered. And yet, this exact point on the map was chosen, abandoned, rediscovered, and rebuilt multiple times, first by local Dacian communities, then by the expanding power of the Roman Empire, and later by Byzantine forces trying to hold together what remained of a fractured frontier. The pattern begins before the Romans ever arrived. Early fortifications appeared here not as a grand city, but as a functional outpost, something placed with intent rather than ambition. Then Rome came, and instead of selecting a new optimized location, they reinforced what was already there. Stone replaced earth, geometry replaced improvisation, but the position itself remained unchanged, as if the decision had already been made long before Roman engineers imposed their order onto it. When the empire weakened and external pressures intensified, Dinagisha was struck, damaged, partially erased. Under normal circumstances, that would have been the end. History tends to abandon what fails. But not here. Instead of fading into obscurity, Dinagisha reappears. Not immediately, not continuously, but persistently. The Byzantines return to the same ground, not to create something entirely new, but to reconstruct what had already been lost. Walls are repaired, not redesigned. Foundations are reused, not relocated. The city does not evolve in a straight line. It accumulates. Each phase of construction sits on top of the previous one, like layers of memory that were never fully erased. The result is not a single coherent structure, but a stack of intentions separated by time yet bound to the same coordinates. This is where the anomaly begins to take shape, because Dinagisha is not located at the most defensible position along the Danube. It is not the highest elevation, nor the most inaccessible terrain. It does not dominate the landscape in the way other long-lived fortresses do. In purely strategic terms, it is good but not exceptional. And yet, across centuries of conflict, migration, and technological change, it is consistently selected as if it were indispensable. That consistency becomes harder to explain the more closely it is examined. Civilizations that did not share continuity of governance, culture, or long-term planning all converged on the same decision. They did not inherit a thriving metropolis that forced their hand. More often than not, what they found was ruin, broken walls, collapsed structures, evidence of failure, and still they chose to build again. The architecture itself reflects this unusual relationship with time. There is no clear final version of Dinagetia, no moment where it reaches a definitive form. Instead, it exists as overlapping fragments. Roman precision embedded within earlier layouts. Byzantine repairs cutting through older geometries. Lines that should align but do not, because they belong to different centuries. It is not a city that was designed once and perfected over time. It is a place that was repeatedly resumed. Even more striking is what does not happen here. For a location occupied across such a long span, there is no dramatic technological leap tied specifically to Dinagetia. No revolutionary urban planning that spreads outward. No identifiable phase where it transforms into a dominant regional power. It persists without ascending. It survives without redefining itself. In most cases, longevity and innovation are linked places that last tend to evolve. Dinagetia resists that pattern. It remains functionally similar across its many lives, as if its purpose never required reinvention. That raises a question that cuts deeper than strategy. Because if Dinagetia was simply useful, it would have been replaced when better options emerged. If it were merely convenient, it would not have been rebuilt after repeated destruction. The cost of reconstruction labor, materials, time suggests that returning here was not the easiest choice. It was the necessary one. There is something else embedded in its geography, something less obvious than elevation or visibility. The Danube at this point is not just a river, it is a corridor, a threshold between regions, a moving boundary that defines access and control. Dinagetia does not dominate the river. It sits at a point where movement can be observed, influenced, perhaps constrained in subtle ways. Not the strongest position, but a precise one. A place that does not announce its importance but enforces it through consequence. Over time, this creates a kind of gravitational pull in history. Not a physical force, but a strategic inevitability. When power shifts, when borders move, when old systems collapse, decisions are made under pressure. And under that pressure, different civilizations separated by language and centuries arrive at the same conclusion. This point cannot be ignored. What makes Dinagetia unsettling is not any single mystery, but the repetition itself. One cycle of destruction and rebuilding can be explained. Two might be coincidence. But over centuries, the pattern becomes too consistent to dismiss as chance. It begins to look less like independent decisions and more like convergence, multiple paths leading back to the same fixed point. And yet, the site never fully transforms into something greater than the sum of its parts. It does not become a capital. It does not anchor an empire. It remains, in a sense, incomplete, as if its role was never to dominate, but to endure, to exist at a threshold where presence mattered more than progress. Perhaps that is the key to understanding it. Dinagetia was not important because it grew into something extraordinary. It was important because it could not be left behind. Every time it was destroyed, the absence it created was felt immediately. A gap in control, a vulnerability in movement, a silence where there should have been structure. And so, it was rebuilt not out of ambition, but out of necessity. History tends to celebrate what advances. The cities that expand, the empires that innovate, the structures that redefine what is possible. But Dinagetia belongs to a different category. It is a place defined not by what it became, but by how often it returned. A location where time does not move cleanly forward, but circles back again and again, insisting on continuity even in the face of collapse. And that leaves a final question, one that lingers long after the ruins themselves have been understood. If a place continues to be rebuilt for over 1,000 years, across civilizations that had every opportunity to choose differently, is it truly a matter of strategy? Or is it something deeper, something embedded in the landscape itself that we still do not fully understand? On the southern coast of Crete, facing the open waters of the Libyan Sea, lies the ancient site of Komos. Today it appears little more than a field of stone foundations overlooking a quiet beach. Yet when archaeologists began systematic excavations in the 1970s, they uncovered something unexpected. Beneath the sand lay the remains of what may have been one of the most important maritime centres of the Bronze Age Mediterranean. Unlike Knossos, Phaistos, or other famous Minoan palaces, Komos was not built to dominate the landscape. It was built to connect worlds. And the deeper researchers dug, the more they encountered a technological mystery that remains unresolved today. How did a civilization more than 3,500 years ago construct and operate a harbour complex whose scale, organisation and international reach appear centuries ahead of what many historians once believed possible? The first clues emerged from the enormous buildings uncovered near the ancient shoreline. Some of these structures were unlike ordinary Minoan houses. One complex stretched more than 50 meters in length. Massive walls, large open spaces and unusual layout suggested that these were not residences but specialized facilities. Archaeologists soon realized that Komos was not simply a coastal settlement. It functioned as a gateway between Crete and the wider Mediterranean world. Imported pottery from Egypt, Cyprus, the Levant and mainland Greece appeared throughout the site. Chemical analyses of ceramics demonstrated that goods were arriving from hundreds and sometimes thousands of kilometers away. Such evidence revealed a level of international commerce comparable to later Phoenician trading ports. Yet it existed during a period when most European societies remained small agricultural communities. What makes Komos particularly mysterious is its apparent role as a harbour. The settlement occupied a strategic position along major sea routes, connecting the eastern Mediterranean. Ships travelling between Egypt, the Near East, and the Aegean would have passed nearby. Yet despite decades of research, archaeologists still cannot fully explain how the harbour functioned. Modern coastlines rarely preserve ancient maritime infrastructure intact. Sea levels change, sediments accumulate, storms reshape entire shorelines. At Komos, the original harbour installations appear to have been altered or buried by thousands of years of geological activity. As a result, researchers can identify the existence of a major port but struggle to reconstruct the engineering systems that allowed it to operate. This problem becomes even more intriguing when one considers the environmental challenges facing Bronze Age sailors. The Libyan Sea is not a sheltered bay. Seasonal winds can generate powerful waves capable of damaging vessels and eroding coastlines. Modern ports often rely on extensive breakwaters, seawalls, and dredging operations to maintain navigable channels. Yet no massive harbour defences comparable to those seen in later Roman ports have been discovered at Komos. This creates a technological puzzle. If large numbers of ships were regularly arriving and departing, how were they protected from storms? Some researchers propose that ancient coastal configurations created natural shelter now lost beneath changing sediments. Others suggest that engineering features remain hidden beneath offshore deposits. Neither explanation has been conclusively demonstrated. The largest buildings at Komos raise even deeper questions. Several scholars have proposed that these structures functioned as ship sheds. If true, they would represent some of the earliest large-scale maritime maintenance facilities known anywhere in the world. The idea is based on the unusual dimensions of the buildings, which seem capable of accommodating long wooden vessels. Yet the evidence remains incomplete. No preserved ships survive within the structures. No definitive launching ramps have been identified. The buildings resemble ship sheds in some respects and differ in others. Consequently, one of the most important questions remains unanswered. Were these among humanity's earliest naval engineering facilities, or were they something entirely different? The ship shed hypothesis becomes even more remarkable when calculations are considered. Reconstructions of Minoan merchant vessels suggest lengths ranging from 20 to 30 meters, with loaded weights potentially reaching several tens of tons. Moving such ships out of the water for repair would have required sophisticated logistical systems. Rollers, sledges, ramps, ropes, coordinated labour forces, and carefully prepared surfaces would all have been necessary. Yet almost none of these components survive archaeologically. The buildings exist, the maritime evidence exists, the ships are known from artistic depictions and indirect remains. The mechanisms connecting these elements have largely vanished. What remains is a technological shadow hinting at capabilities that archaeologists can infer but not directly observe. Another mystery concerns the management of trade itself. Komos appears to have handled enormous quantities of goods moving across the Mediterranean. Storage areas, warehouses, and imported materials indicate continuous commercial activity. This raises an organizational challenge. Modern ports depend upon written records, inventories, manifests, schedules, and bureaucratic administration. The Minoans possessed writing systems such as Linear A, yet that script remains undeciphered. As a result, archaeologists can identify the physical infrastructure of trade, but cannot read the instructions that governed it. Thousands of storage jars have been discovered throughout Minoan sites. Commodities such as olive oil, wine, textiles, metals, and agricultural products likely passed through Komos. But the methods used to track, allocate, and distribute these resources remain hidden behind an undeciphered language. The technological sophistication implied by this trade network becomes even clearer when compared with other Bronze Age societies. During the 2nd millennium BCE, maritime routes linked Egypt, the Levant, Cyprus, Anatolia, and the Aegean into a vast interconnected system. Komos occupied a strategic position within that network. goods arriving from distant regions demonstrate that sailors regularly crossed hundreds of kilometers of open sea. Some voyages exceeded 1,000 kilometers. Navigating such distances required knowledge of winds, currents, seasonal weather patterns, and celestial observations. Yet no surviving Minoan navigation manuals exist. Unlike later Greek and Roman writers, the Minoans left no readable descriptions explaining how they crossed the sea. Their success is visible through archaeology, but the knowledge that made it possible remains largely invisible. Even the construction methods used at Commos continue to provoke debate. The settlement survived for centuries despite earthquakes, changing coastlines, and fluctuating political conditions. Builders repeatedly modified structures, expanded facilities, and adapted to environmental challenges. Geological studies indicate that southern Crete experiences significant seismic activity due to its position near active tectonic boundaries. Maintaining large coastal buildings in such an environment would have required practical engineering solutions. Yet because most structures survive only as foundations, many details of their upper architecture remain unknown. Archaeologists can reconstruct outlines and dimensions, but the complete technological system behind these buildings has disappeared. Then came the decline. During the late Bronze Age, the Minoan world experienced profound disruption. Earthquakes, political upheaval, changing trade patterns, and the broader instability affecting the Eastern Mediterranean transformed regional networks. The eruption of Thera, one of the largest volcanic events of the ancient world, occurred within this era of upheaval. Although direct links between the eruption and Commos remain debated, the wider consequences were enormous. Trade routes shifted, power centers changed, maritime connections weakened. Eventually, the great harbour complex lost the role that had once made it indispensable. Yet Commos did not disappear entirely. Centuries later, new inhabitants established sanctuaries on the site. Archaeologists discovered evidence of Phoenician influence, alongside Greek material culture. This continuity creates another mystery. Knowledge appears to have persisted across cultural transitions. Maritime traditions survived. International contacts continued. Somehow, fragments of earlier expertise remained embedded within the region long after the original Minoan system had faded. The story of construction is supposed to be gradual, unstable shelters, becoming structured villages, crude walls evolving into engineered cities, with every stage leaving behind traces of error, transition, and refinement. But La Almoloya challenges that entire narrative. Perched on a dry hilltop in southeastern Spain, this Bronze Age settlement, dated roughly between 2,200 and 1,550 BCE and attributed to the El Argar culture, presents something deeply unsettling. A system that appears already complete, not evolving, not experimenting, just functioning, as if the process that should have led to it had already happened somewhere else. La Almoloya was systematically excavated in the early 21st century by researchers from the Autonomous University of Barcelona, building on earlier surveys of Argaric hilltop settlements, and what initially appeared to be another fortified Bronze Age site quickly distinguished itself through an unusual level of structural clarity that did not match the expected developmental patterns of the time. Stratigraphic analysis revealed occupation layers consistent with mid-2nd millennium BCE habitation, yet the architectural coherence across those layers suggested minimal redesign or adaptation over centuries, which is highly atypical when compared to other settlements of similar age. Radiocarbon dating of organic remains confirmed a relatively narrow occupation window, approximately 6 to 7 centuries, yet within that period, the site exhibits a level of planning more commonly associated with later, more complex societies, and when compared to contemporaneous settlements across Iberia, many of which display irregular growth, spatial improvisation, and continuous architectural adjustment, La Almoloya instead appears intentionally designed from its earliest phase, with no clear transitional forms and no primitive prototypes beneath the final structures, as if the first version we see is already the final version. The most striking structure uncovered at La Almoloya is a large rectangular hall, often interpreted as an early form of political or assembly space, measuring approximately 70 square meters and containing stone benches lining the walls that could seat around 50 individuals in a structured and highly organized arrangement. And this is precisely where the anomaly begins to take shape. In Mesopotamia during the same period, political authority was typically embedded within temple complexes or palace structures that were hierarchical and often inaccessible to collective participation, while in ancient Egypt, centralized power expressed itself through monumental architecture, designed to reinforce authority rather than facilitate discussion. Yet here, in a relatively small settlement in Iberia, there exists a space that appears optimized for visibility, acoustics, and structured gathering in a way that implies coordinated interaction rather than passive observation. The geometry is deliberate, with a central open area functioning as a focal point and a seating arrangement that ensures all participants face inward, suggesting an understanding of spatial dynamics linked to governance or at least organized decision-making. And more importantly, there is no evidence of earlier versions of this space, no smaller or less refined hall, no irregular gathering area that gradually evolved into this design, meaning it appears fully conceptualized from its inception, not as the result of trial and error, but as a complete idea executed immediately. The true mystery of La Almoloya lies not in its layout, but in the behavior of its materials, because the site's architecture relies heavily on rammed earth, compacted clay, and natural gypsum-based plasters, materials that, under typical environmental conditions, are expected to degrade relatively quickly, especially in a region like southeastern Spain where the climate is semi-arid, characterized by strong temperature fluctuations between day and night, and periodic rainfall that accelerates cracking, erosion, and long-term structural failure in earthen construction. And yet, despite these conditions, sections of flooring and wall bases at La Almoloya remain remarkably intact after more than 3,500 years, preserving not only their structure, but also their geometry to a degree that is difficult to explain through conventional expectations of Bronze Age construction. Micromorphological studies of the floor layers reveal dense compaction and carefully layered construction sequences, with some surfaces exhibiting hardness levels approaching that of weak concrete, which implies repeated compression techniques or precise moisture control during the building process, both of which require a level of material understanding that is not clearly documented for this period. In experimental archaeology, attempts to replicate similar density and durability using reconstructed Bronze Age methods have produced inconsistent results, often failing to achieve the same level of cohesion and long-term stability observed at the site, when compared to contemporaneous adobe structures in the Near East, which were built using broadly similar base materials but have often degraded into indistinct sedimentary layers over time. Losing their original shape and structural definition, La Almoloya stands out as an exception rather than a rule, and even in environments more favorable to preservation, maintaining flat, continuous surfaces over millennia without stone reinforcement is extremely rare. At La Almoloya, however, floor planes remain level across measurable spans, wall junctions retain structural coherence, and the adhesion between material layers shows minimal separation, suggesting that the builders were not simply using available materials, but controlling them with a level of precision that appears disproportionate to the technological framework we associate with the Bronze Age. This leads to a critical question. Were these builders intuitively mastering principles of soil mechanics at a level that modern reconstruction still struggles to replicate? Or were they applying a standardized construction method that has not survived elsewhere in the archaeological record with the same clarity? The paradox is not that the materials themselves are advanced, but that their performance exceeds expectations without any visible evidence of the developmental process that would normally produce such results. Directly beneath the assembly hall, archaeologists uncovered a burial that introduces an additional layer of complexity to the site's interpretation, where inside, a large ceramic vessel were the remains of two individuals, a man and a woman, accompanied by an extraordinary collection of silver artifacts, including a finely crafted diadem that immediately drew attention due to both its craftsmanship and symbolic implications. The significance of this burial lies not only in the wealth it represents, but in how that wealth is distributed, because the diadem, a clear marker of status and authority, was associated with the woman rather than the man, challenging long-standing assumptions about gendered power structures in Bronze Age Europe, where authority is typically interpreted as male-dominated. Chemical analysis of the silver indicates a high level of purity and suggests controlled extraction and distribution networks within the Argaric culture, pointing to an organized economic system capable of managing valuable resources with precision. Furthermore, the placement of the burial directly beneath the central political space suggests a deliberate integration of authority, ancestry, and architecture. Unlike many other ancient societies where elite burials are spatially separated into tombs, necropolises, or designated sacred zones, because here, power is not set apart from daily function, but embedded within it, structurally and symbolically at the same time, making the building itself not just a place of gathering, but a physical manifestation of authority that rests quite literally on the individuals buried beneath it. The layout of La Almoloya reveals a level of planning rarely seen in settlements of the same period, with terracing clearly separating residential and functional zones, indicating intentional design rather than organic growth. Defensive positioning relies on elevation and visibility, prioritizing efficiency over monumental construction. However, the most striking feature is the absence of developmental layers. There are no simpler structures beneath more complex ones, as typically found in archaeological sites. From its earliest phase, the settlement already displays a complete spatial organization, suggesting it did not gradually evolve but appeared in an almost finished state. This leads to two possibilities. Either the knowledge was developed elsewhere and introduced here, or the transition occurred so rapidly that it left little trace, both of which challenge the conventional model of gradual societal evolution. If a society can build something this complete without leaving behind any trace of how it evolved, do you think we are missing part of human history or misunderstanding it entirely? Share your thoughts in the comments below. In 1926, during Benito Mussolini's massive urban redevelopment projects, workers demolishing old buildings in the heart of Rome unexpectedly uncovered something hidden beneath the modern city. As excavation continued, archaeologists revealed 4 ancient Republican temples, sections of paved streets, monumental foundations, and parts of the massive Theatre of Pompey complex. The site became known as Lago di Torre Argentina. At first glance, the ruins appeared to be another collection of Roman remains, but decades of excavation would reveal something far more intriguing. Beneath the crowded streets of modern Rome lay evidence of engineering capabilities that continue to challenge archaeologists and structural experts today. The temples date from approximately the 4th to the 2nd centuries BCE, meaning some structures have survived for more than 2,200 years. Yet many of the technologies that made such survival possible remain only partially understood. One of the greatest engineering puzzles begins with the location itself. Lago di Torre Argentina sits within the ancient floodplain of the Tiber River. Modern engineers recognize floodplains as some of the most difficult environments for large-scale construction. Soft sediments, seasonal flooding, groundwater fluctuations, and long-term soil movement create serious structural risks. Even today, projects built on similar terrain often require deep foundation systems, reinforced concrete piles, soil stabilization techniques, and continuous monitoring. Yet Roman builders erected monumental stone temples, weighing thousands of tons on this challenging landscape over 2 millennia ago. Archaeological investigations reveal massive foundation platforms extending deep below the visible ruins. These foundations distributed enormous loads across unstable ground with remarkable effectiveness. The mystery is not simply that the structures were built. The mystery is how Roman engineers determined where and how deep to build without geological surveys, drilling equipment, computer modeling, or modern soil analysis. The survival of these foundations through centuries of floods, earthquakes, urban development, and environmental change suggests a level of practical geotechnical knowledge that remains difficult to fully reconstruct. For comparison, many medieval structures built more than 1,000 years later suffered severe settlement problems. Yet portions of the foundations at Largo di Torre Argentina remain remarkably stable. Beneath the temples lies one of the most famous yet least understood technologies of the ancient world, Roman concrete. Known as opus caementicium, this material formed the backbone of Roman engineering. Samples recovered from structures throughout Rome demonstrate extraordinary durability. Modern concrete often begins showing significant deterioration after 50 to 100 years, particularly when exposed to moisture and environmental stress. The concrete used in Largo di Torre Argentina has survived more than 2,000 years. Scientific analysis has identified several key ingredients: volcanic ash known as pozzolana, lime, stone aggregates, and water. Yet knowing the ingredients is not the same as understanding the technology. Recent materials science research has shown that some Roman concrete contains microscopic lime clasts, capable of promoting self-healing reactions when cracks develop. These reactions can generate new mineral growth that helps seal damage. The question is whether Roman builders intentionally engineered these properties or accidentally discovered them through centuries of experimentation. No surviving technical manuals explain the process. No engineering documents reveal quality control procedures. No written instructions describe how mixtures were optimized for different construction environments. The concrete remains, but the knowledge behind it largely disappeared. Water was both Rome's greatest resource and one of its greatest threats. The Tiber River provided transportation, trade routes, and fresh water, but it also flooded frequently. Historical records indicate numerous major floods throughout Roman history. Some inundated large sections of the city. Yet the temples of Largo di Torre Argentina remained functional for centuries. Excavations have revealed evidence of sophisticated drainage systems beneath the site, including channels, stone-lined conduits, elevated platforms, and engineered surfaces designed to redirect water flow. However, only fragments survive. Much of the original hydraulic network has either been destroyed, buried beneath later construction, or remains inaccessible beneath modern Rome. This creates a fascinating problem. Archaeologists can see the results, but they cannot see the entire system. Computer reconstruction suggests that Roman engineers may have integrated the temple complex into a broader urban drainage network connected to roads, sewers, and nearby public infrastructure. If true, the site represents part of a citywide hydraulic machine operating at a scale comparable to some modern municipal systems. Yet significant portions remain hidden beneath the modern city, leaving many questions unanswered. The temples discovered at Largo di Torre, Argentina were not constructed at the same time. Some were separated by centuries. Different governments, different architects, different political periods, and different construction teams contributed to the complex. Despite this, modern laser surveys reveal impressive geometric consistency. Walls align with extraordinary precision. Foundation platforms maintain carefully controlled orientations. Structural elements exhibit accuracy that often differs by only centimeters across distances of dozens of meters. Today, such precision is routinely achieved using GPS systems, laser scanners, electronic total stations, and computer-assisted design software. Roman engineers possessed none of these technologies. Their primary surveying instrument was the groma, a relatively simple device consisting of crossed arms and hanging plumb lines. The question is not whether the groma worked. The question is how such apparently simple tools achieved results that continue to impress modern surveyors. Some researchers argue that Roman surveying techniques have been underestimated. Others suggest that generations of accumulated practical experience created levels of accuracy that written sources fail to capture. Whatever the explanation, the precision remains remarkable. Every visible ruin at Largo di Torre, Argentina represents a transportation challenge. Columns weighing multiple tons had to be quarried, transported, positioned, and aligned. Stone blocks were moved through crowded urban environments without trucks, cranes, hydraulic lifts, or powered machinery. Experimental archaeology has demonstrated that Roman lifting devices were capable of extraordinary performance. Reconstructions of Roman treadwheel cranes indicate lifting capacities ranging from several tons to more than 6 tons under ideal conditions. Yet many questions remain. How are operations coordinated? How many workers participated? How are loads stabilized? How are precision placements achieved without modern measuring equipment? The problem becomes even more impressive when considering the scale of Roman construction elsewhere. The same civilization that built the temples of Largo di Torre, Argentina, also constructed the Pantheon, aqueducts spanning dozens of kilometers, and amphitheaters capable of holding tens of thousands of spectators. The technologies clearly worked, but the details of their operation remain incomplete. Adjacent to the temple complex once stood one of the greatest structures in Republican Rome, the Theatre of Pompey. Completed around 55 BCE, it was the first permanent stone theatre ever built in Rome. Ancient sources estimate a capacity between 15,000 and 20,000 spectators. Today, only fragments survive beneath modern buildings. This creates an extraordinary archaeological mystery. Ancient writers describe the theatre. Excavations reveal portions of its foundations. Modern technology can map buried remains. Yet no complete architectural plans survive. No engineering reports exist. No construction manuals explain how the project was organized. The building represented one of the largest construction undertakings of its era. Yet much of the technical knowledge required to create it vanished with the Roman world. Ironically, modern researchers often understand the final structure better than the engineering process that produced it. At the center of Rome, Italy, rising approximately 40 meters above the Roman Forum, stands Palatine Hill, one of the most famous archaeological sites in the world. According to Roman tradition, this was the place where Romulus founded Rome in 753 BC. Archaeological investigations began as early as the Renaissance, but major scientific excavations accelerated during the 19th and 20th centuries. What researchers expected to find were the remains of imperial palaces. What they discovered instead was something far more intriguing: evidence of enormous engineering systems hidden beneath centuries of ruins. Today, archaeologists estimate that the imperial complexes covering Palatine Hill once occupied more than 150,000 square meters. Beneath the visible ruins lies a labyrinth of tunnels, foundations, reservoirs, drainage networks, and structural systems that continue to challenge modern understanding of ancient engineering. Most ancient capitals were constructed on relatively stable terrain, but Palatine Hill presented a completely different challenge. Its slopes were irregular, its geology varied from one section to another, and large portions required extensive modification before major construction could begin. Yet Roman emperors transformed the hill into the political center of the empire. Massive complexes such as the Domus Flavia, Domus Augustana, and later imperial palaces stretched across the summit. Modern engineers understand the difficulty of constructing large buildings on uneven terrain because every structure generates pressure on the ground beneath it, and the larger the structure, the greater the risk of settlement, cracking, or collapse. Some walls on Palatine Hill still stand nearly 20 meters high after almost 2,000 years. Even more remarkable, many of the supporting foundations remain structurally stable despite centuries of earthquakes, erosion, and human activity. The mystery is not that the Romans built these structures, but how they calculated the necessary support systems without modern geology, structural analysis software, or advanced surveying equipment. One of the greatest surprises uncovered by archaeologists was the scale of the underground infrastructure. Beneath the palaces lies a vast network of corridors, service passages, storage chambers, drainage systems, and structural galleries. Some tunnels extend for hundreds of meters beneath buildings weighing thousands of tons. In modern architecture, underground construction beneath large structures requires extensive calculations regarding load distribution, ventilation, groundwater control, and long-term stability. The Romans somehow achieved these objectives nearly 2 millennia ago. Researchers continue to debate the original purpose of many underground passages. Some appear to have been used by servants, others likely transported supplies, and certain sections may have functioned as maintenance corridors for water systems and utilities. Yet, significant portions remain poorly understood, and the complete engineering logic of the underground network has never been fully reconstructed. Summer temperatures in Rome regularly exceed 35 degrees Celsius, making the maintenance of comfortable living conditions inside enormous stone structures a major challenge. Evidence from Palatine Hill suggests that Roman architects employed sophisticated passive cooling techniques. Thick walls absorbed heat during the day and released it slowly at night. Courtyards created airflow patterns that encouraged natural ventilation. Water channels running through certain areas may have contributed to cooling effects, while underground chambers likely helped regulate temperature fluctuations. Modern sustainable architecture increasingly employs similar principles. Buildings designed for energy efficiency often rely on thermal mass, natural airflow, and evaporative cooling rather than mechanical air conditioning. This remarkable similarity raises an important question. Did Roman architects gradually discover these principles through centuries of experimentation, or did they possess a more systematic understanding of environmental engineering than historians currently recognize? Perhaps no technological mystery on Palatine Hill is more famous than Roman concrete. Many structures on the hill contain concrete mixtures that have survived for nearly 2,000 years. Some sections remain stronger than many modern equivalents, despite constant exposure to weather and environmental stress. Scientific studies have revealed complex combinations of lime, volcanic ash, aggregate, and mineral reactions occurring over long periods. Recent research suggests that certain Roman concrete formulations may possess self-healing properties, with tiny cracks triggering chemical reactions that gradually seal damaged areas. For comparison, many modern reinforced concrete structures are designed for service lives of roughly 50 to 100 years before major repairs become necessary. Palatine Hill demonstrates durability on a completely different scale. Scientists can identify the ingredients and analyze the chemistry, yet many aspects of the manufacturing process remain uncertain. The exact methods used by Roman builders continue to generate debate among material scientists worldwide. Water was essential for imperial life. The palaces required drinking water, fountains, baths, kitchens, gardens, and sanitation systems, yet Palatine Hill stood above much of the surrounding city. Archaeological excavations have revealed extensive hydraulic infrastructure, including reservoirs, lead pipes, channels, distribution systems, and storage facilities. The challenge was maintaining reliable water delivery across varying elevations. Modern water networks rely heavily on pumps, pressure controls, and monitoring systems, technologies that Roman engineers lacked. Nevertheless, they successfully supplied vast quantities of water to the imperial complex. Researchers still debate the exact operation of several hydraulic components. Some pipe networks appear more sophisticated than expected, while certain reservoirs may have served multiple engineering functions simultaneously. Even after decades of investigation, a complete understanding of the water management system remains elusive. Many of the surviving structures on Palatine Hill showcase Roman mastery of arches and vaults. These curved architectural forms allowed builders to create enormous interior spaces while reducing dependence on dense forests of support columns. The engineering challenge is significant because every arch must distribute forces correctly, and every vault must channel weight toward carefully positioned supports. Small errors can trigger catastrophic failure, yet many Roman vaults have survived earthquakes, fires, invasions, and centuries of neglect. Some structures continue to stand despite the loss of large sections of supporting material. Modern engineers can model these systems using advanced software, but Roman builders achieved similar results through methods that remain only partially understood. Before construction could begin, the Romans had to measure the terrain. This seemingly simple task may represent one of the greatest mysteries of all. Building complexes covering tens of thousands of square meters required accurate alignment, elevation measurements, drainage planning, and structural positioning. Today, such tasks are performed using GPS systems, laser scanners, digital mapping equipment, and computer-generated models. Roman engineers possessed none of these technologies. Yet archaeological surveys repeatedly reveal extraordinary precision throughout the Palatine complexes. Walls align correctly, drainage gradients function efficiently, and structural relationships remain remarkably consistent. The instruments used by Roman surveyors are known in general terms, but the level of precision they achieved remains difficult to explain fully. Among the most intriguing discoveries on Palatine Hill are the remains of the Domus Transitoria, the first grand palace associated with Emperor Nero. Although much of the structure was destroyed during the Great Fire of AD 64, excavations revealed evidence of remarkable engineering sophistication. The palace featured marble decorations from distant provinces, advanced water features, carefully designed lighting effects, and elaborate interior spaces intended to manipulate perception and movement. Some researchers believe the palace incorporated combinations of water, reflection, architecture, and natural light to create immersive visual experiences unlike anything previously seen in Rome. Unfortunately, much of the structure vanished before detailed documentation could survive. The surviving remains hint at technological capabilities that historians can only partially reconstruct. discovery came quietly. Unlike buried cities revealed by chance or catastrophe, Ulaka was never truly hidden. It was simply ignored. Rising across a granite plateau in central Spain, the site was first systematically documented in the late 19th and early 20th centuries, when Spanish archaeologists began mapping Iron Age hill forts across the region of Avila. What they found did not fit expectations. Instead of a modest fortified village, Ulaka extended across nearly 70 hectares, placing it among the largest known Vitonian settlements in the Iberian Peninsula. Early surveys noted massive defensive walls stretching over 3 kilometers, carved features embedded directly into bedrock, and an absence of architectural hierarchy that would typically define a city of this scale. It was not just large, it was structurally inconsistent with what a pre-Roman society was supposed to build. Excavations that followed were limited but revealing. Initial campaigns in the early 20th century uncovered domestic zones, stone foundations suggesting clustered habitation, though without uniform planning. Mid-century investigations identified sections of fortification, confirming the use of large granite blocks assembled without mortar, relying instead on weight, friction, and geometric placement. Later archaeological work, particularly in the late 20th and early 21st centuries, focused on specific anomalies. A monumental staircase carved directly into granite bedrock, and a massive sculpted stone structure interpreted as a ritual altar. Each phase of excavation added fragments of understanding but never a complete system. No inscriptions clarified ownership. No tools were found that matched the scale of construction. No clear administrative center emerged. The more Ulaka was studied, the less it resembled a conventional ancient settlement. The first major contradiction begins with its location. Positioned at an elevation approaching 1,500 meters, Ulaka exists in an environment defined by exposure, strong winds, seasonal cold, and limited access to stable water sources. For comparison, contemporaneous settlements such as Numantia occupied defensible yet resource-accessible terrain, integrating proximity to rivers and agricultural land. Coastal hill forts like Castro de Baronia leveraged marine resources and moderate climates. Ulaka does neither. Its plateau offers visibility, but at the cost of sustainability. And yet, evidence suggests occupation spanning multiple generations between the 4th and 1st centuries BCE. A settlement of this size, under these conditions, should not persist unless its purpose extended beyond simple habitation. The second contradiction is physical. The stone. Across Ulaka, granite dominates not as scattered debris, but as structured architecture. Granite, with a compressive strength exceeding 100 megapascals, is notoriously resistant to shaping. Even with iron tools, quarrying and refining such material demands significant labor investment and technical coordination. Yet at Ulaka, large blocks, many estimated to weigh several tons, are positioned with relative precision. Walls maintain alignment without mortar. Surfaces show signs of deliberate shaping, though without the regular tool marks typically associated with advanced metal implements. More striking still is the integration between natural bedrock and constructed form. Instead of fully extracting and relocating material, builders appear to have modified the landscape in place, carving directly into granite to produce functional structures. Nowhere is this more evident than in the staircase. Carved into a solid outcrop, the steps ascend toward a flattened upper platform. Each tread is uneven, but intentionally so, suggesting adaptation to natural contours rather than imposition of a rigid design. The act of cutting into granite at this scale implies repeated, controlled impact over extended periods. Experimental archaeology suggests that shaping even a single cubic meter of granite Using basic iron tools can require dozens of labor hours. At Ulaka, the volume of modified stone extends far beyond isolated features. It represents a sustained effort, organized, purposeful, and technically consistent. And yet, no concentration of tools has been recovered to support such activity. No workshops. No debris fields typical of large-scale quarrying. The evidence of work exists. The evidence of the workers' methods does not. Comparative analysis deepens the anomaly. In Mediterranean contexts, large-scale stone construction such as that seen in Greek or later Roman architecture relies on standardized block production, visible chisel patterns, and clear quarry sites. Even in earlier megalithic traditions, transport and placement often leave identifiable traces: ramps, tool fragments, or partially worked stone. Ulaka diverges. Its construction is less about imposing geometry onto material and more about negotiating with it. This has led some researchers to propose that the builders employed hybrid techniques combining limited metal tooling with controlled fracturing, thermal stress, or even the strategic use of natural fissures within the granite. None of these hypotheses, however, fully account for the consistency observed across the site. Beyond the stone itself lies the question of function. Among the most discussed features at Ulaka is the so-called altar, a large sculpted granite block positioned at an elevated point within the settlement. Its form is ambiguous, stepped, smoothed in sections, and oriented toward open space. Traditional interpretation assigns it a ritual role, possibly linked to Vettonian religious practices. Yet direct evidence, such as remains of offerings or repeated burn layers, is minimal. The structure's placement, however, is deliberate. From its position, large portions of the surrounding landscape are visible, including distant horizons. This has led to alternative interpretations suggesting observational or calendrical functions. While speculative, such theories highlight a broader pattern at Ulaka: structures that appear functional but resist singular classification. The issue of water intensifies the mystery. No permanent rivers or springs are present on the plateau. Archaeological surveys have identified carved basins and depressions that may have served as reservoirs, capturing seasonal rainfall. But basic hydrological estimates indicate that rainfall alone would struggle to sustain a large, permanent population, especially during dry periods. If Ulaka supported thousands of inhabitants, as its size might suggest, then either its population fluctuated significantly or additional water management strategies existed. Some researchers have proposed the possibility of now lost channels or transport systems linking the plateau to lower elevations. Others argue that the site functioned as a seasonal aggregation center rather than a continuous settlement. Neither explanation is fully supported by current evidence. Social structure presents yet another divergence. Across Ulaka, no clear central authority is visible in the archaeological record. There is no dominant structure, no palace, no administrative complex. Instead, habitation appears distributed clusters of similar scale dwellings without obvious hierarchy. In contrast, many ancient urban systems, even at early stages, exhibit some degree of centralization, whether political, religious, or economic. Ulaka's layout suggests a different model, a network rather than a core. This raises the possibility that the Vettones, or at least the community occupying Ulaka, operated under a decentralized system, one capable of organizing large-scale construction without concentrated power. And then, the ending. By the 1st century BCE, Ulaka is abandoned. There are no widespread burn layers indicating destruction, no mass graves, no abrupt structural collapse. The site appears to have been vacated in an orderly manner. This timing coincides with the expansion of the Roman Empire into the Iberian Peninsula. a process that restructured settlement patterns, drawing populations toward more accessible, economically integrated regions. It is possible that Ulaka's inhabitants relocated, adapting to a new system. But if so, they left behind a site that had required immense effort to construct, without dismantling, without repurposing, without clear transition. Do you think Ulaka was a failed experiment left behind? Or evidence of a system we still don't fully understand? Share your thoughts in the comments below. The old town of Gadames did not emerge from a single excavation, nor was it revealed by a dramatic archaeological breakthrough. Instead, it was slowly understood, pieced together through fragmented accounts left by European explorers of the 18th and 19th centuries, who described it as an impossible oasis city. Only in the 20th century did systematic architectural surveys and early thermal studies begin to document what was actually happening inside its walls, revealing a pattern that could be measured rather than merely observed. Field measurements showed temperature differences of up to 10 to 15 degrees Celsius between shaded interiors and the surrounding desert, where surface temperatures could exceed 45 degrees Celsius, a gap too large to be explained by shade alone. What initially appeared to be a conventional Saharan settlement gradually revealed itself as a controlled environmental system, one that seemed disproportionately advanced compared to the simplicity of its materials. From above, Gadames appears chaotic, a dense cluster of irregular forms without symmetry, alignment, or visible planning logic. Yet when mapped in detail, the layout reveals an extreme density combined with intentional enclosure that defies expectations of organic growth. Streets are not open corridors but covered, compressed, and interconnected pathways that form a continuous, three-dimensional labyrinth, eliminating direct exposure to sunlight across large portions of the city. Unlike Roman urban models such as Timgad, where rigid orthogonal grids prioritize clarity and expansion, or even medieval Islamic Medinas that evolve organically but retain partial openness, Gadames pushes enclosure to an extreme limit, suggesting that exposure itself was treated as a problem to be solved. This creates a contradiction within conventional urban theory, which assumes irregular layouts are the result of unplanned growth and therefore produce inefficiencies such as dead ends, poor ventilation, and uneven sunlight distribution. Yet in Gadames, the irregularity appears to enhance environmental performance rather than degrade it. Studies of airflow in dense built environments demonstrate that narrow, enclosed passages reduce wind speed while increasing pressure differentials, allowing controlled air movement instead of turbulent flow. And in Gadames, this principle is scaled across the entire Medinat, where covered streets filter and slow hot desert winds, stabilizing temperature and preventing sudden heat spikes while maintaining continuous circulation, behavior that aligns more closely with engineered systems than with accidental urban evolution. The most intensively studied component of Gadames is its network of covered streets, which extend far beyond isolated shaded alleys and instead form a continuous environmental envelope punctuated by carefully positioned openings that regulate both light and airflow. Thermal measurements consistently show that these corridors maintain temperatures significantly lower than exposed desert streets, often by 10 degrees Celsius or more, a difference that cannot be attributed solely to reduced solar radiation, but instead points toward a combined system of shading, ventilation, and material response. In modern engineering, replicating such passive cooling requires detailed simulations involving solar angles, thermal conductivity, and airflow modeling, often using computational fluid dynamics to predict how air will behave in confined geometries. Yet Gadames achieves comparable results through spatial configuration alone. The placement of openings is particularly revealing, as they are neither decorative nor random but appear at calculated intervals that allow hot air to escape upward while limiting direct solar penetration, generating a slow vertical movement of air that resembles what modern engineers define as the stack effect. Comparable techniques can be observed in Persian windcatcher systems, such as those found in Yazd, where towers capture and redirect airflow into interior spaces. But the crucial difference lies in scale and integration, because while windcatchers operate at the level of individual buildings, Gadames distributes the same principle across an entire urban fabric, effectively turning the city itself into a single passive cooling device, a level of systemic integration that remains difficult to explain through incremental trial and error alone. The materials used in Gadames appear deceptively simple, consisting primarily of mud brick, lime plaster, gypsum, and organic fibers, all of which are widely available and commonly used across North Africa and the Middle East. Yet their combined behavior within this Medina suggests a level of control that exceeds ordinary vernacular construction. Walls are often built to substantial thickness, sometimes exceeding 0.5 meter, creating a high thermal mass that absorbs heat slowly during the day and releases it gradually at night, producing a delayed heat transfer effect that stabilizes indoor temperatures despite extreme external fluctuations. While the principle of thermal mass is well understood today and widely applied in energy-efficient architecture, experimental data from Adobe structures indicate that achieving optimal thermal lag requires precise calibration of wall thickness, density, and surface treatment, because insufficient thickness allows rapid heat penetration, while excessive thickness leads to heat retention that raises nighttime temperatures. In Gadames, however, this balance appears consistently maintained across different structures, suggesting that builders were not merely applying known materials but were operating within an optimal range that maximizes performance. Comparisons with other Adobe-based settlements, including those found in Morocco, show effective insulation but rarely the same level of systemic consistency, reinforcing the idea that in Gadames walls, streets, and roofs do not function independently but interact as components of a unified thermal network, a level of integration that resembles engineered systems more than isolated architectural decisions. Gadames is not only organized horizontally but vertically, forming a layered structure in which different levels perform distinct environmental and social functions, with enclosed lower streets providing shaded circulation, middle levels serving as thermally stable living spaces, and upper rooftops offering exposure to light and air. This vertical zoning creates a natural convection system in which hot air rises from the lower levels and escapes through rooftop openings while cooler air remains trapped below, establishing a passive circulation loop that regulates temperature without mechanical assistance. In modern sustainable architecture, similar effects are achieved through atriums, ventilation shafts, and solar chimneys that require precise calculations of pressure gradients and temperature differences, yet in Gadames, no such calculations are recorded, even though the system operates with remarkable efficiency. Adding to this complexity is the integration of social structure within the same spatial framework, as historical accounts indicate that rooftops formed a separate circulation network, primarily used by women, effectively creating a dual-layer city where movement patterns align with thermal behavior, suggesting that environmental engineering and social organization were not independent considerations, but were designed as a single interdependent system. The deeper analysis progresses, the more one unresolved issue becomes impossible to ignore, which is the complete absence of a documented framework explaining how Gadames was designed, as no surviving manuscripts describe its layout, no engineering treatises outline its principles, and no transitional stages demonstrate a gradual evolution from simpler forms. Despite this absence, the city exhibits controlled thermal gradients, integrated airflow systems, material optimization at an urban scale, and spatial organization aligned with environmental forces, all of which typically require formal knowledge systems in other historical contexts. Roman engineering, for example, is documented in the writings of Vitruvius, while Persian hydraulic systems are preserved in detailed records, yet Gadames exists without an equivalent body of theory, creating a gap between observable performance and recorded knowledge that remains unexplained. Gadames does not stand entirely alone, but fits into a broader pattern of ancient constructions that appear more optimized than their technological context would predict, from the precision of Andean stonework to the hydraulic sophistication of the Indus Valley. Yet it differs in a critical aspect, because it does not address a single engineering challenge, but simultaneously resolves multiple environmental constraints, including extreme heat, intense solar radiation, limited water availability, and sand-laden winds. What makes this particularly significant is that these solutions are not isolated innovations, but are integrated into a unified urban system in which every component contributes to overall performance, suggesting a level of systemic thinking that is rarely attributed to pre-industrial societies.